Next.
Professor R.V. Sir, Archives, Professor O.D. Martinez sir, Professor Manjula Das ma'am, Controller of Examinations, Soha Doonchuk University, Professor Renu Sharma ma'am, and Apul Narayan sir, Convener of EAC 2024. Please make a moment available and commenting. Hereby I request all our dignitaries to have their seats. And once again, I welcome you all in AMSE 2024. Now, without any further delay, our first item on the agenda is our traditional inaugural ceremony. We acknowledge our reverence for wisdom and for the lighting of our lamp. I invite all the dignitaries and delegates on the dais to be honored as we officially commence our day.
We can also do.
Thank you everyone. Now once again I would like to request each one of you to please get up for the solo anthem.
Siksha
begin with some greetings and welcome address by Professor Sunita Chand. She is presently working as a professor and head of the Department of Mathematics. She has a teaching experience of more than 25 years. She is also a gold medalist of our AMSE batch and has also taught in AMSE. PhD, qualitative study of partial differential equations. With this, I request Professor S. Chand to come on the dais for the welcome address. Thank you, Kuruda.
Respected Professor R.P. Sharma, Dean MIT, Arunachal Pradesh. Respected Chief Guest, Professor O.D. Matinle, Stellenbosch University, South Africa. Respected Guest of Honor, Professor Manjula Das, Controller of Examination, Siksha Anusandhan, Dean to the University. Esteemed Professor Renu Sharma, Additional Dean Student Affairs, and Dr. Atul Narayan Dev, Convener, AMSE 2024, distinguished invited speakers and delegates of the dais, heads of the departments, invitees, members of electronic and print media, my dear colleagues, friends, ladies and gentlemen. It is a matter of pride and great honor for us to organize the third International Conference on Applied Mathematics in Science and Engineering, AMSE 2024, during 25th to 27th July 2024. I take this opportunity to welcome all the delegates and participants of this conference from different corners of the world on behalf of the organizers and co-organizers. The conference is organized by the Center for Data Science and Department of Mathematics, ITER, Siksha Anusandhan, Dean to the University, and is co-organized by the Basic and Applied Science, MIT Arunachal Pradesh. The Center for Data Science comprises of around 37 faculty members and 2 supporting staff, and the Department of Mathematics comprises of 40 faculty members and 4 supporting staff. Both the center and the department have been consistently on their march for academic excellence. All the faculty members of both the center and the department are actively involved in research in various fields. Coming to AMSE 2024, this is the third international conference being organized in this series. The first international conference on applied mathematics in science and engineering, AMSE 2019, was held during 24th to 26th October 2019 and was jointly organized by Siksha Anusandhan, Dean to the University, and MIT Arunachal Pradesh. Around 110 participants had attended the conference. The second international conference on applied mathematics in science and engineering, AMSE 2022, was held in online mode during 24th to 26th March 2022 and was organized by Siksha Anusandhan, Dean to the University. It was attended online by around 150 participants. Today we are embarking on a 3-day journey as we begin the third international conference on applied mathematics in science and engineering, which will span a period of 3 days from 25th July to 27th July 2024. This conference will be on hybrid mode. The objective of this conference is to provide a platform for researchers and professionals from both academia and industry to exchange the latest knowledge and experience in various fields of applied mathematics and data science. The conference will provide the researchers an opportunity to present their novel findings in front of the scientific and mathematical community. We have several invited talks by distinguished keynote speakers over the span of 3 days, which will enhance our knowledge and ideas about diverse fields. There will be paper presentations which will open up new vistas and give us great knowledge on various areas on which the researchers are currently working, and it will be very valuable for all the participants of this conference. Last but not the least, about our beautiful city, Bhubaneswar. It is the capital of our state, Odisha. It is known as the city of temples. It is very scenic and beautiful. So I hope your stay in Bhubaneswar will be enjoyable and pleasant. With this hope, I would like to end my address. And
Thank you, Dr. Ashton. We are very pleased by your welcome address. Now we have Professor Anusandhan Sharma, NIT Arunachal Pradesh. He was awarded the PhD degree in Fluid Dynamics by the Department of Mathematics, University of Rajasthan. He is currently working as a member of Board of Governors, Senate, and Professor of Mathematics, Department of Mechanical Engineering, National Institute of Technology, Arunachal Pradesh. He is actively engaged in research in the field of fluid mechanics. His research work has covered boundary layer flows. Dr. Sharma has published more than 100 publications in peer-reviewed national and international journals. He is a life member of more than 1.5 dozen national and international academic societies. He was elected Joint Secretary of the Executive Committee of ISTAM, IIT Kharagpur. He has organized 2 one-month annual foundation school, 6 international and 3 national conferences. Dr. Sharma has participated in more than 200 national and international seminars, conferences, and has also presented research papers. He has given many invited lectures, sessions, and chaired and attended over 15 ATM workshops, summer school, and an induction program. So with this, I request Dr. R.P. Sharma sir to please be.
Namaskar. Respected Professor P.K. Nanda, Vice Chancellor, Siksha Anusandhan University, Professor O.D. Matani, Chief Guest of the AMSE 2024, Professor Department of Applied and Computational Mathematics, University South Africa, Professor Sunita Chand, Head Department of Mathematics, Professor Mandela Das, Professor of Mathematics and Controller of Examination, Professor Venu Sharma, Additional Dean, ITER, Siksha Anusandhan University, and Dr. Apul Narayan Dev, convener of the conference, and Professor S.R. Misra, my dear friend and younger brother. Ladies and gentlemen, guests, distinguished speakers, and delegates, it is my distinct honor and pleasure to welcome you to the 3rd International Conference on Applied Mathematics in Science and Engineering, hosted by Siksha Anusandhan University and co-organized by NIT Arunachal Pradesh. Here in the vibrant city of Bhubaneswar, it is known as Temple City of India. As we gather here today, we are united by a common purpose to explore the profound impact of applied mathematics on science and engineering. This conference serves as a platform for sharing cutting-edge research, boosting collaborations, and advancing the boundaries of knowledge in these critical fields. Over the next 3 days, we will engage in discussion that have the potential to shape the future of our disciplines and contribute to solving some of the most pressing challenges facing our world today. First and foremost, I would like to express our heartfelt gratitude to the online committee for their tireless efforts in bringing this event to fruition. Their dedication and meticulous planning have ensured that we are all here together, ready to embark on this intellectual journey. I would also like to extend a warm welcome to our keynote speaker, session chairs, and panelists who have arrived from various parts of the world to share their expertise and insight. Your presence here is a treatment to the importance of this conference and the value of the collaboration across borders. I would like to once again express my gratitude to all of you for being here today. Your presence and participation are what make this conference a success. Let us seize this opportunity to learn, share, and inspire one another as we work towards advancing the frontiers of applied mathematics in science and engineering. I wish you all the productive and rewarding conference filled with engaging discussion, fruitful collaborations, and lasting friendship. Together, let us pave the way for the future where mathematics continue to drive innovative and create better world for all. I am also grateful to the President of the Siksha University, Sri Manoj IMSE, and my friend Dr. S.R. Misra. I will quote one key poet who I awarded the Nobel Prize for literature in 1971. One poem: "You start dying slowly if you do not travel, if you do not meet, if you do not listen to the sounds of life, if you do not appreciate yourself, you start dying slowly. When you kill yourself, when you do not let others help you, you will start dying slowly. If you become a slave of your habits, walking every day on the same path, if you do not change your routine, if you do not be a different color, or you do not speak to those you don't know, you start dying slowly. If you avoid to feel pressure and their turbulent motions, those which make your eyes glisten and your heart beat fast, you start dying slowly. If you do not take a step for the uncertain, if you do not go after a dream, if you do not allow yourself at least once in your lifetime to run away from sensible advice, don't let yourself die slowly. Do not forget to be happy.
Thank you, everyone. Next, we have our chief guest, Professor Odi Mackey. He is an eminent professor of applied mathematics and computation with more than 26 years of professional experience in South African universities. He is currently affiliated with the Faculty of Military Science at Stellenbosch University, South Africa. Additionally, he acts as a visiting distinguished professor to several other universities within and outside the African continent. Professor Makinde held the position of Senior Professor and Chair of Postgraduate Studies at the University of Technology, South Africa. His Professor and Head of the Applied Mathematics Department at the University of Limpopo, South Africa. Professor Makinde has received numerous awards for his contributions to science, engineering, technology, and innovation in Africa and beyond. Professor Makinde's research has contributed immensely to the upliftment of many scholars in the field of mathematical sciences and to postgraduate training. He organized several conferences, workshops, and symposia within and outside the African continent and delivered keynote research papers at several national and international conferences and workshops worldwide. He has an extensive record of research and academic collaboration with several faculties and universities in countries. He is a certified member of International Association of Engineers. Professor Makinde is presently the Vice President of the African Mathematical Union for South Africa region. He served as the Secretary General of the African Mathematical Union, the Vice President and General Secretary of the South African Mathematical Sciences Association, a founding academic advisory board member of the African Institute for Mathematical Sciences, an associate member of the International Center for Theoretical Physics, and an associated member of the National Institute of Theoretical and Computational Sciences in South Africa. With this, I request Professor O.D. Makinde to please be here for his address.
I will start by first thanking God for giving us this opportunity for us to meet and share academic ideas in this turbulent world. I know all of us know that the world we are living is not as great globally in terms of contribution to science, engineering, and technology because of many things happening all over the world. And we know that science, engineering, technology is universal. And we work as researchers, we work in unity. Whether you are based in America, in Africa, in Asia, we are the same. So we thank God that I share. Secondly, I would like to thank the president of this institution. Very old woman. The man that is, with my pledging, the man that is extremely interested in science, engineering, and technology and development of this institution, not that he's the president only, but he has that passion. So you have got a great man in your midst, your president. Let me also show my appreciation to the Vice Chancellor of this institution. We are very lucky to have a Vice Chancellor that also supports. They are always very busy. We researchers, most of us don't like administration and administrative position. We always want to be now with a laptop and computer and so on. For the Vice Chancellor to spare his time to come and deal with us, it's a great privilege because we have various meetings, various things they have to deal with. Thank you very much for honoring and supporting this great site towards science, technology, and advancement of India and the world in general. I would like to appreciate the Director of Academics. She has been a very wonderful and great woman. Her hospitality is unparalleled. Showed us great hospitality. Thank you very much for that. I'm very grateful. And I extend my appreciation to the local organizing committee chairman, Professor Happel. He always communicates with me in South Africa every time. I always raise him very effective. One of the pillars of this conference. Very active, very effective. Welcome us, receive us, making sure that everything is going well. And we really appreciate your efforts and continue that way. Thank you very much for everything you have done. And I thank Professor Sharma, a very great mathematician, and I've been many papers because I received many papers and the travel of so many dollars, and the teacher of his contribution, and keep it up. That's why I say academically we are united, researchers work to promote science, technology, and innovation globally. Thank you very much for keeping up that work. And I will not forget my good friend. For the past 11 years, Professor Siksha, we have been collaborating, we have been working together. In fact, we used to communicate through WhatsApp, video call, working together, do so many things. That thing I know we have different times to. At times we hear that every time in South Africa, and here it is different time or something. We'll be working, communicating, okay, this, that. Keep it up. And I'm very, very happy for his progress. Making a very fast-like progress in things. I thank you for your contribution to this SOA and for the international network that has developed for this issue. Thank you very much. Now, all my colleagues that are here and my let me stand up, okay. I was never I was, thank you very much. So, I've been a great leader for the department and you have done a great work. Please keep it up because when you look at what is going on now, without your support, there is no way. Because we need administrative support for academic to function properly. You have shown a lot of leadership in this area, and that's why we are having all these documents you are seeing with us. And you have also contributed to the process of this conference in a very great way. Thank you, and I thank everyone that are here, both colleagues, researchers, professors, students. We are all the same. There is no discrimination in academia. There is no big or small. We are all learning. As students we are learning, as professors we are learning. We learn from each other. Let us take it very serious. The more you learn, the more you know. The more you know, the more you can contribute to society. But if you don't learn, then you stop to learn, it's time you start going down. Let us keep on learning and making meaningful contribution to society. On behalf of also African Mathematical Union, that I'm one of the, I can say, the leaders in that organization for the continent. And saying that we are having open arms to collaborate. Collaboration is extremely important with Indian researchers. Some of us have been doing it and we have been preaching it across Africa. and many have been collaborating. That collaboration is the way out. Nobody has monopoly of knowledge. Therefore, when we collaborate, we can change this turbulent world. It's only in science, engineering, technology, research that you don't see fighting. Because we are looking forward to develop, to make life easy for society. Innovative products, using our idea. So we are very grateful that the population of those in that group are increasing. Let us keep increasing the population and make our impact on this planet that we are. Thank you very much. I'm very grateful for inviting me and bringing me here. And Chief, yes, and I'm at your service. For the conference, little I know, we can share it together. What you know, I can learn from you. We are all here to learn. Let us make use of this. Use it effectively to learn, to collaborate, to network. And so that by this time next year, you can look back and see what you have achieved in this conference. Thank you very much. Thank you, Vice Chancellor. Thank you, everybody. God bless you all. Thank you.
Thank you so much, sir. We are highly grateful with your presence. We have Professor Manjula Das, a professor in mathematics and has been associated with ITER since 2005. She assumed the role of controller of examination at Suwadi to the university. Prior to this, she served as a faculty member in Department of Mathematics. Then she became the head of Center of Applied Mathematics and Computing. Now it's Center for Data Science. She also successfully managed the responsibility of professor in charge of examinations at ITER. Professor Das has approximately 32 years of teaching experience in mathematics at various institutions, including the PG Department of Statistics. Her research focuses on statistical analysis of socio-economic issues, operation research, and fluid dynamics. Under her headship, many international conferences like AMSE 2019 and AMSE 2022 were conducted successfully. From the Department for Center of Data Science and Mathematics, Professor Das is a live member of various educational societies. So with this, I request Ma'am to be here.
Very good morning to all of you. Esteemed Chief Guest, Professor Odin McKinley, Stellenbosch University, South Africa. Honorable Vice Chancellor, Professor P.K. Somali University. Respected Professor Rakesh Sharma, Dean NIT Additional Dean. Additional Dean ITER Professor Renu Sharma. Respected Professor J.C. Das. Respected invited speakers, guests, officials, faculty members, dear students, and participants. It's truly a matter of joy and happiness for me attending to this conference as guest of honor, because I am an old member of both the departments, Department of Mathematics as well as Center for Data Science. As a former member of the Department of Mathematics and head of Center for Data Science till 2022, I have had the privilege of being deeply involved in previous conferences. Two conferences were conducted in 2019. One is of national level, another is AMSE, international level. And another one we have conducted in 2022, which was online mode because of the pandemic. These conferences have set high standards for academic excellence and have been a testament for the dedication and hard work of our organizing team. I sincerely congratulate Professor Dr. Opal Nagande for his dedication and sincere effort in organizing all these conferences. I remember while discussing about the first conference to conduct it, initially he was a bit hesitant because at that point of time he was new to this institute as well as he was thinking of the challenges he might face during the conferences. However, with the unlimited support of our authority, management and university staff, the conference was organized successfully. And that success paved the way for the subsequent conferences. Now, as I gather for this AMSE 24, I hope the commitment to fostering an environment where both theoretical and applied aspects of mathematics are explored, bridging the gap between theory and practice. We are privileged to have so many distinguished speakers and keynote speakers as well, researchers also, presenting their novel findings to stimulate the meaningful debate and enhance our collective knowledge. The essence of the conference lies in exchanging ideas, sharing experience, fostering collaborations, driving innovations, and advancing in the respected areas. So that's why I encourage the young researchers to engage themselves actively in these conferences, which are going for 3 days, so that these aspects can be achieved by them fully. Once again, I congratulate the convener, Dr. Rakul, with his team for the relentless effort in conducting this conference, and I hope this conference AMSE 24 will be a big something success. So thank you all.
Thank you so much, ma'am. Next we have Professor Renu Sharma, senior member IEEE, has done her PhD in electrical engineering. She is working as additional Dean Student Affairs and Professor in Department of Electrical Engineering, Siksha Anusandhan, Dean to be University. She had been head of Department of Electrical Engineering for 7 years. She is a senior member of IEEE, life member IE India, member IET, life member ISC, life member IAAC, joint secretary IEEE Bhubaneswar subsection. She is featured as one of the top 2% of scientists in the world as per Stanford University for the year 2024. Her research areas are smart grid, soft computing, solar photovoltaic systems, power systems scheduling, evolutionary algorithms, and wireless sensor networks. He has published around 160 journals, book chapters, and conference articles of international repute. He has organized several national and international conferences. He is guest editor of special issues in International Journal of Power Electronics in the Science. He served as reviewer for IEEE Transaction Journals, LBZ Journals, Springer Journals, and Taylor and Francis Journals too. Guest editor of special issue in the International Journal of Innovative Computing and Application. So with this, I request Professor Renu Sharma ma'am for her address.
Thank you so much. Honorable Vice Chancellor, Siksha Anusandhan, Dean to be University, Professor P.K. Lamisa, Chief Guest, Professor O. D. Markandeep from Stanford University, respected Professor R.K. Sharma, Dean NIT, Arunachal Pradesh, guest of honor, Head of Examination, Goa University, Professor Manjula Das Madam, Organizing Chair and Head of the Department, Professor Sunita Chand, Convener of the Conference, Dr. Apul Beg, Head of the other departments, distinguished guests, esteemed faculty members, and enthusiastic participants. Good morning and a warm welcome to all of you to this conference. It is my privilege as Additional Dean, Student Affairs of the Faculty of Engineering and Technology at Siksha Anusandhan Dean to be University to address you on this one of the year's occasion, the inaugural ceremony of Third International Conference on Applied Mathematics in Science and Engineering. This conference, organized by the Center of Data Science and Department of Mathematics in collaborations with NIT Arunachal Pradesh, signifies a significant milestone in our academic journey. It brings together the brilliant minds from and across the globe to deliberate on the applied mathematics, a field of crucial and critical for tackling the complex challenges of our time. I extend my heartfelt gratitude to esteemed guest, Chairperson, Selvan University Professor Odri Margate, for gracing us with his presence on this occasion. Professor, your presence not only honors us, but also inspires our academic community to strive for excellence in the research and education. I am equally delighted to welcome our Vice Chancellor, Sir, Professor Vikenanda, Sir, whose visionary leadership continues to steer SOA University towards academic distinction and holistic development. Sir, your unwavering support and guidance propel us forward in our mission to nurture the talent and foster the innovation. We are also privileged to have today with us guest of honor, Madam Manjula, who is Controller of Examinations at SOA University, who have played a pivotal role in shaping the academic landscape of our university. And your dedication and commitment to academic integrity sets high standard for all of us. I must acknowledge the pivotal role of Professor R.K. Sharma sir from NIT Arunachal, and Dr. Sunita Chan, head of the department and the convener of this conference, Apul Dev, whose tireless effort along with organizing this conference with the challenges what they face, they overcome the challenges, day to day the conference progresses, and the day has come that we are sitting here advancing the frontiers of knowledge in truly commendable manner. Institute of Technical Education and Research ITER, Faculty of Engineering and Technology, a constituent institute of Siksha Anusandhan deemed to be university, is committed to excellence in education and research and stands as a beacon of knowledge in the realm of higher education. Here we are fostering to conduct environment for interdisciplinary research and innovation with a state-of-art infrastructure, world-class facility, and diverse student community. We aim to empower our students to become the global leaders and change makers. Today's conference underscores our university commitment to foster industrial collaborations and promoting interdisciplinary collaborations with research in applied field of mathematics. It provides a platform to the scholars and the researchers, as the eminent speakers have already told, and the practitioners to exchange their idea to explore new horizons and foster partnership that transcend geographical boundaries. As we embark on this journey of the knowledge of creations and dissemination, let us reaffirm our commitment to harness the power of mathematics to address the global challenges and improve the quality of life all over the globe. I wish all the participants a fruitful deliberations and memorable experience at the 3rd International Conference on Applied Mathematics of Science and Engineering. Thank you all, Janet.
Thank you so much, ma'am. Next we have Professor P.K. Nanda, Vice Chancellor of SOA, deemed to be University. He received his PhD from IIT Bombay and was a faculty member at NIT Rourkela from 1986 to 2007. After that, he relocated to SOA deemed to be University, where he is serving as the university's Vice Chancellor. Before this, he was the Pro-Vice Chancellor and Dean of SOA deemed to be University. He is the Chairman of the Board of Management of SOA. Currently, he is directing the research in the Image and Video Analysis Laboratory. He has published 103 papers in various journals and conference proceedings and has authored 3 research books and 3 book chapters. He was Chair of IEEE, GRSS Society, Kolkata Chapter, and Vice Chair of the IEEE Computational Intelligence Society. He received the Bharat Jyoti Award from the Indian International Friendship Society in 2012 and the Odisha Technopride Award on 15 September 2013 from the Evergreen Forum of Odisha on Engineers Day. He is a fellow of IET India and a senior member of IEEE. With this, I request Professor P.K. Nanda sir for his address.
Good morning, everybody. The guest of this informal conference, Professor O.D. McIntyre, Professor Department of Applied and Computational Mathematics, Post University, South Africa, Professor R.P. Sharma, Dean NIT, Himachal Pradesh, also Professor of Mathematics, Dr. Manula Das, who controls the examination, and also the staff on the Anusandhan, Additional Dean, Institute, Anusandhan University, Dr. Punita Chand, Head of the Department of Mathematics, Pari, Head of the Department, Chief Coordinator of Center for Data Science, Professor Apun Dev, honor of this conference, Professor Das, and all the professors, distinguished guests, speakers, and delegates, scholars, and students of this university. Ladies and gentlemen, at the outset, I once again welcome you to this university, Anusandhan University. I think I congratulate also Dr. Opuna and Dev and his entire team for organizing the series of this conference. This is the third in the series. I think this COVID, they had the online conference organized. I think I wish that we continue this series, and SO University will be proud to have such kind of series of conferences in this sector. As far as the university is concerned, we have been very proactive, urging every department and faculty members to organize conferences in different fields. Just last Saturday, we ended a conference in terms of conference in agricultural science jointly with the Center for Climate Science, Climate Smart Agriculture. Similarly, we have conducted many conferences in different campuses. More than 500 conferences we have conducted last 10 years in our university. More than 72 international conferences also we conducted. And the university started with this institute itself, and with maybe 3 faculty and 3 students back in 1996. Campus here in 2000, and then it spread, and it actually grew over the years to become a university in 2007. After 2007, the focus changed to focus on R&D and also the innovation and the collaboration, joint research, back to the society to extension activities. The focus of the university, where the mandates of the university have been followed. And with this, the university view currently we have around 17,000 students and 600 faculty members at this university. We have 4 campuses. The university visiting this campus and house inside the city. We expanded to the other campus 2, 3, and 4, and offering almost all professional courses in this university. It is a truly multidisciplinary university, which means to be multidisciplinary education and research university in future, the new NEP category. That's the objective of this university. And over the years, we have in 2009 we had research. Now the research ecosystem has evolved, and over the years we could achieve success. And 2009 we had only 300 publications to our credit, and now we have 12,830 publications in Scopus Index, Journal Science Conferences, and 7,000 publications in Web of Science. And our index also grew. The faculty members and the students also are contributing substantially to this research. As a result, the average impact factor of our universities. So the highest is 200. The New England Journal of Medicine by Medical Science, and also many other faculty are publishing. Started with engineering, added of course the different institutes like management, hotel management, pharmaceutical science, and biotechnology, management science, nursing, mental science, medical science, and have also added law, agriculture, and 2020 veterinary science. Like this is the right platform for collaboration. And we are evolving and we have collaborated with 139 institutes from our country and abroad. And also now our focus is we are connecting with the industry and into collaboration institutes as well. Over the years, if you look at the contribution in different fields, we have established dedicated centers, 20 dedicated centers. The last center we established Center for Quantum Science and Technology is the new mission of Government of India, Quantum Mission of Government of India, and there also we have collaborated with 14 institutes and scientists. So this is growing, and also prior to that, we set up a Center for Industrial Biotechnology. Centers we have established 2004 itself, and prior to that, we were making different research centers. As a change in focus of this discipline of the engineering, right, globally. So there is a paradigm shift in global framework that the entire field has to change. The core branches of engineering, computer science, undergone a sea change. So one of the focus was, I think, more focus was data science, the buzzword is AI, and cyber security, IoT. All these buzzwords came into, and actually the entire globe reoriented itself. So that time also our university focused on change and established a couple of years back the Center for Data Science. This specifically also we have established other centers like Center for IoT and cyber security, also AI, to cater to the current or keep pace with the current demand and current need of the entire globe. So this data science we have inducted faculty to cater to computer science department. Nevertheless, mostly from the either from the computer science or from mathematics, who is having a background on data science. With computer science, most of the applications and all data science is mathematics. So therefore, this was a center in the name created as a sub-department kind of a thing, which is attached under the Department of Computer Science. So they do, in fact, impact teaching to the Department of Computer Science students and carry out research in the respective fields. So as a joint, I think most close relationship with both the Department of Mathematics and Data Science, and I could see that their collaborative effort is growing in this kind of organizing conferences. And many of the young faculty who have inducted in data science, they are also very active. I think Dr. Apuli is one of them, who is, I think, spearheading this series of conferences, and I request Dr. Apuli also to continue the same nature. As far as the mathematics is concerned, this is ubiquitous to the all disciplines. I think there is a misnomer that mathematics is not required, but mathematics is at the bottom strata of everything. So therefore, and this is quite evident in the current one because of the application of data science, whether it is management science and AI is a buzzword for all disciplines in the across the world. And you use it and you feel the response of that. And all this is based on the underlying theory of mathematics. And definitely the applied mathematics as such, the pure mathematics people are thinking differently, had a different misgivings about mathematics, but when the mathematics application was quite evident and tangibly to the society, then there are a lot of attractions to the applied mathematics. So therefore, applied mathematics plays a pivotal role and attract different kind of scientists, engineers, technocrats in all fields almost. So I think we talk about the AML today, there is no field I think left where this is not applied. So data science is another approach of that. Now the industry also needs skilled people in these areas. So therefore, applied mathematics have to be strong in these areas. Mathematics is the backbone of this. But nevertheless, to popularize mathematics, we need to do a lot more things like conferences, workshops, seminars, where we do kind of the bent house for the applicants of the potential of different things. Could it be science, could it be engineering, technology, could it be agricultural science, could it be veterinary science. I think there is no discipline or university where statistics is not applied. I think medical technology, medical science, and dental science, and veterinary science, they will depend on specific. So similarly, management science is also dependent on data science itself. So therefore, this is kind of a now the mathematics as is ubiquitous and visible and acceptable by the all the community of these different disciplines, and which was kind of a taboo to the different people that mathematics is a different thing. So I think this conference definitely will kind of discuss, deliberate, and join together and promote further the areas of applications where we can kind of achieve some kind of tangible outcomes out of this application of mathematics. And we're sure the people who think that mathematics is a taboo will now know more in this kind of disciplines. So I will once again welcome all the delegates from across the globe, in the nation, country and abroad, and also the delegates and the speakers from all over the globe to participate in this conference and contribute. I wish that the collaboration I could see that there is no Dr. Mishra and Dr. Sarma and Dr. Patel, and more collaborations with more academics happen so that this is an area of collaboration and we also foster collaboration, encourage faculty members to collaborate. Therefore, we have signed MOUs with the universities and also appointed very urgent professors from abroad as well as in our country so that the joint effort which happens for the quality research and joint contribution live sessions from congratulatory team and welcome everybody for this great deliberation. Young and body researchers in this.
Thank you so much, sir. We are highly pleased. Next, we have Dr. Anusandhan, convener of AMSE. He completed his PhD from Guwahati University, and his research interests are theoretical studies on basic plasma, dusty plasma, quantum plasma, and mathematical method and fluid dynamics. He joined his institute in January 2016 and has received International Travel Grant from Department of Science and Technology in 2017. Currently, he is an associate professor of Center for Data Science. He has published 40 SCI journal papers and 6 book chapters. He also published one book named Shock-Wave Phenomena in Dusty Plasma. He was the editor of AIT Conference Proceedings of volume number 2819. In 8 years of teaching career, he has conducted 2 international conferences as a convener and 3 international webinars on behalf of Suwadi Today University. With this, I request Dr. Dev sir to begin.
Good morning, all. So, at the end of the inaugural session of the third International Conference in Applied Mathematics, Science and Engineering, AMSE 2024, I, Dr. Okuna, and to take the liberty of proposing the vote of thanks. So, it is our great pleasure to introduce Professor Odi Martin from Stellenbosch University, South Africa, our esteemed chief guest, to take his precious time to visit us, the SWA family, and grace the conference with his presence. Thank you, sir. We also thank Professor R.P. Sharma, the Dean, NIT Women's College, for the inaugural address and acting as a co-organizer for this conference. Thank you. We thank Professor P.K. Nandal, the Vice Chancellor of Siksha of Anusandhan University, for the presidential address on this auspicious occasion. Thank you, sir. We are grateful to Professor Manju Controller of Examination, Siksha of Anusandhan University, who act as the guest of honor at this conference. We would also like to express our gratitude to Professor Renu Sarno, Additional Dean of ITER, for her motivation and support. We are honored to have many esteemed faculty members from renowned universities of India and abroad who gracefully agree to present their cutting-edge research findings by acting as keynote speakers, invited speakers in this conference. Thank you to all the main speakers and participants. The most important person who we can never forget, and without who support this conference would not have been possible, is our reward founder, president of Siksha of University, Honorable Professor Anusandhan Naik, sir. We express thanks and offer our gratitude to him for his unconditional support for organizing such great events. Sincere thanks are expressed to Professor Manas Kumar Pandit, Director of ITER, for giving continuous support in all aspects. We extend our thanks to Professor Sunita Sant, Head of the Department of Mathematics, Siksha of University, as well as the organizing chair of this conference, for her relentless motivation. Thank you, ma'am. We also extend our thanks to Dr. Manoj Pari, Chief Coordinator of the Center for Data Science, Siksha of University, as well as the co-organizing chair of this conference, for his unwavering support. Thank you for all support. On behalf of the Center for Data Science and Department of Mathematics, Siksha of University, we extend our heartfelt gratitude to all the participants from India and abroad for gracing this event with your presence. Last but not the least, I would like to express my gratitude to the technical committee members who gave their tireless effort for all the activities of the conference. I would also like to express my gratitude to all the faculty members from the Center for Data Science and the Mathematics, Department of Mathematics, who have made this event happen. So thank you to all. Thank you very much.
Thank you so much, sir. Now I would request everybody to proceed for the high tea break on the second floor of the same building, and after 15 minutes we will meet here for the technical session.
Hello. आपण ट्रेन येतो आपण ट्रेन आपण केंद्र ରହିବେ ନା
Once again, I welcome you all in the technical session of AMSE 2024. At the first, we have Professor Ori Makinde as our speaker. He is an eminent professor of applied mathematics and years of professional experience in South African countries. Professor Makinde has received numerous awards for his contributions to science, technology, and innovation in Africa and beyond. He also won the Chancellor Award for Outstanding Research Excellence at Stellenbosch University in 2019, the Outstanding Reviewer Award from the Journal of Central South University in China in 2020, and the 2021 Obama Prize for Distinguished International Research Award, as well as the 2022 African Mathematical Union and Pan-African Congress of Mathematician Award for Outstanding Researcher and Mentorship. Professor Makinde is on the editorial board of several reputable academic journals. He has also served as a reviewer for many reputable international academic journals worldwide. He published over 650 research papers in several reputable high-impact international journals. His research covers a broad range of topics including fluid mechanics, nanofluid dynamics, heat and mass transfer, hydrodynamic stability, dynamical systems, thermal science, combustion theory, biomathematics, and epidemiological modeling, computational mathematics, and improved perturbation techniques. Professor Makinde's research has contributed immensely to the upliftment of many scholars in the field of mathematical science research and postgraduate training. With this, I request Professor Odi Makinde to please start with his content.
years about followed by along the line. I know I have before time. So thank you very much to share some of our work. We have done and post and continue to do value engineering of developing new mathematical techniques tackle all the problems from scientific and engineering. Many techniques and approaches and methods markets now. Developing more robust methods will be able to understand dynamics, what's going on in the and once you understand it, you can control it and put what you want. So this talk is going to focus on how to analyze non-real problems, AMSE and the approximation techniques. And the outline of what I'm going to talk about in the next 45 minutes or up to 40 minutes. I'm going to give some brief introduction, look at the title and talk about AMSE and the approximation techniques. And the other part of it is science and engineering problems. So I'll give a brief introduction on that, then the first applications and go to some model formulations and illustrations, how to apply the methods to tackle some problems and get some results, then some numerical results and conclusion. Model problems in engineering and science. When you are for situation, you have to use it. Stochastic will introduce. When you are dealing with problems, you always get differential equations. That differential will be PD or ODE. And if you have ODE, there are ways of transforming PD because the analysis of ODE is well known. So you can use what you know to determine what you don't know. So now, in general, when you model problems in science and engineering, you are going to get a differential equation in context of the dynamical system. Context of the dynamical system. And if you have get this, then can be the parameter that control your system. This function here can be a non-linear function of this. This parameter may be a set of parameters. So you can say, suppose we have this, and the problem is not here. The dynamics of the model which you obtain after you formulate the model to be value conservative is going to be controlled by the parameter that you have there. If parameter changes and system is not here, there will be bifurcation taking place. And if bifurcation takes place, the problem may go from stable to unstable. and there will be some stability analysis you have to do. You know the conditions under which a particular solution can be obtained or can exist. So all these can be done when you have modeled your problem. But to solve this problem and get all that, there are so many methods, numerical, analytical, all kinds of methods to deal with it, depending on the model you get. Now, when you do that, normally, when the problem is highly nonlinear, the first easiest way to look at it is like parameter dependent. It's okay, let me turn it to linear automation techniques. That is why you know that it's okay, solve it by series solution methods. So we can apply this issue of our series or part failure series. In short, you can get failure series for no linear problem. But the disadvantage is that the series solution you get, so we are going to have what you will obtain, and go back there, what you have here as a series solution, only weekly, example weekly nonlinear problem for small parameter of the plan that you have there. And you cannot even get the solution up to infinity, you only get partial sum. Which means your solution will not actually be valid for the nonlinear problem you are solving. And don't make it almost linear to get some idea. But the problem is not linear. Now, when you have this partial sum, the radius of convergence of the partial sum for those in undergraduate, you talk of series, radius of convergence, there are 10 duration of convergence and all those things. You can see the validity of the result will be very, very small compared to the real problem you are solving. Now, in order to progress further, that's what we call Pade, who was a student of Harvard, a PhD student of Harvard. Pade did his PhD in 1992. What he did is to study how can I move this partial sum further, this solution series further, to make it more applicable. And it's now what we call Pade approximation for his PhD. But the problem there is that Pade approximation is not the partial sum to the quotient series, the numerator and denominator, which are all functions of the parameter. And using that, you can also do analytical continuation of the result. You can obtain the singularity that is present in the system. By taking the denominator you have here, set it to 0 and solve for that one. Then we need to know the singularity in the system. But you have to generate more per day, because if you have a partial sum of 5 times, find it 10 to 10 times, 50 times, and compare until you see the one that is consistent in the singularity will be the one that actually is singular which can control the system. And looking at this type of thing, he analyzed it, did a lot of analysis on that to see how the solution of this is better than using ordinary partial sum, like using Pade series. Now, I put there some of the limitations of Pade also in what I put on the board there. Then AMSE, who was the supervisor of Pade, now say, look, I have an idea. This series, this quotient series, is the first order linear in the dependent variable. According to the first order linear function of U. This because which is very interesting. Looking at this, UL plus like this. take this one call the one you have here, this one E, this one Q. Take this to multiply this. You have this times that equal to what you have here. I mean, put it inside the other, so it's like a linear in U. And looking at this, how I said, why can't we make it a polynomial in U? Extend it, a polynomial function, independent variable. But when you do that, remember, we start from here, you convert it to here, which is per day. You can now increase it to higher order. How I suggest that, how I can now work on that, and now generate higher order per day approximation, which will give you a better result than per day approximation. Can you see how this tree goes gradually here? Now, note that, and this is higher order, you can see here, this is higher order. Now I have to do this function for n minus 1 until now stand here. And we call this one algebraic Hamilton per day approximation, approximate. Now give you a partial sum, you can transform it to this. And if you analyze this, you get all the characteristics of that non-linear problem. This will solve this. But the problem now is that you need to obtain this coefficient. Coefficient, all these n, and all the coefficients of this u. And you calculate it from the initial partial sum you have. You have to do a lot of getting a matrix and solving them using matrix, turning them to a linear system and get all the coefficients and be able to obtain a line that. Then another thing works from there. Because if you plot this, because when the problem is non-linear, this has more than one solution. That's one of the facts. Solution is not unique. The solution exists. For non-linear problem, uniqueness is none, but the existence is there. That solution. You can have 2, 3, 4, 5, 6, 7 solutions. But whichever one you want to obtain depends on the condition you put. Which one is stable here? Under certain conditions, if it's stable under the condition, then you get that one. So because of one difference of non-linear and the existence and the problem when you solve them, but the existence of solution. Now, when you plot this solution for this algebra, you get various solution branches of the system. For all solution branches, you have to take note that when you drive your car, you are coming to where? You are coming here, you can't be here at the same time in another place. So you must car can go to anywhere. You can drive to anywhere. But if you are at one place, you can't be in another place at the same time. So one solution, you must obtain one, the other one, you have to do stability for you to get the one you want. What are the conditional ways the one you want is achievable? So we look at that, and improvement from this algebra is what we call differential approximate. Then Albert now said, okay, let's see. We have algebraic approximate. Which we have here, can we turn this u function to be x derivative with respect to the parameter? So to replace this with x derivative of this function u, and the other one n minus 1 derivative, and continue like that, we are going to work with what we have there is a variable coefficient. And the coefficient here will be your function of lambda and so on. Then you are going to have a ordinary differential equation with variable coefficient, and other ordinary differential equation, which you now generate from partial sum. Now partial sum, you now plot it to this, then this one now becomes what you have the total function of n now is now a derivative. So when you do that, the advantage of it is that you generate this, the coefficient of the highest order. You can generate the order 2 or order 3 or order 4 of you can generate Hamilton differential formula of higher order. The question of higher order equating to 0 will give the singularity. And that makes it easy. And it, as accurate as possible, that we can get in for any methodology, even give you better accuracy, and get you all the similarity you can get to the problem. So, based on this idea, and I work on this as okay, we used to teach our undergraduate students differential equation with coefficients that are not constant. Second order with non-variable coefficients. That's very okay. Solve this equation in series solution method. Ordinary singularity, regular singularity, kind of thing, irregular. We give them conditions to obtain variety in the system by taking that. So that's okay. Suppose I forget I generate second order homogeneous ODE variable coefficients. And I take the coefficient of the highest order, second order, following what was in the two students doing differential equation. Okay, also analyze the problem in the problem. Make it third order problem for second order. So I use that and it gives you a very fantastic result. You will see what is going to happen now. Now, from here, let's see. Okay, from this, what I did is to now start this one. And now generate this based on those ideas. And they were published 1999, 2004, 2005, and lot of work has been done with application even up to 2024. Now, what did I do there? Based on all those information, which I deleted. And that's okay. Suppose I have this partial, you see, it is well known that if your partial sum, total of now this of this, and this delta here is your exponent of singularity, and that is the singularity. If this one, suppose this delta is not 0, 1, 2, it's a fraction. It's a fraction, then you can have a singularity when lambda is lambda c. Then it is not a fraction, it's on this form, this is this, and that's the singularity. Now, based on this idea, suppose you are giving, you get a nonlinear problem to solve. This is partial sum you obtain, which can obtain easily, based on many parameters in the system, and you manipulate it in a way that can generate partial sum. When you do that, what do we do here? I convert this to this. You can see you have this algebraic approximate. And also differential approach. You convert it to this one is constant, function of lambda. Lambda is parameter, and you have this u and put 1. This one is 1, that is your is u. This one is the derivative, like I put it here. So if you generate this also u, you generate this and you like this u, this one is when you use u, you have differential approximate. But if you use this one, I mean, you have differential approximate, but if you take it like u cube and so on, you are going to have a algebraic approximate of order 3. Here you have differential and take it like this, which is second order ODE. This exponent of singularity, you can obtain it compared to this, you obtain exponent to this. Let's see some of the test results. Test results to see whether it's working. This idea whether it's working. Now, I take under this function. Now I'm not going to engineering problem now. I take under the function which you have there. Suppose you have g of x in the research question here. X minus lambda is for alpha. Alpha can be a fraction. Now, it's easier for us to generate Taylor series using Mercury mathematical. You can generate Taylor series. If you want under 5 or under 6, you can have this and forget it. Suppose you are given this partial sum. It's impossible for you to reconstruct this function back. You don't get it up to infinity. That's the research question now. That question, I say again, you only partial solve. You don't know this function. But to start with, I assume I know this function, I find it Taylor Swift, and then I calculate it. Now, can you go back to get this one back in the exact form? Can you get the exact one back? And that's, if you can answer that, then you'll be able to solve too many problems that you have this and get something close to the exact as your solution. So to do that, let me give you an example. The example we have here is the dx suppose 1 minus x over 3 raised to power half. If x is 3, that's singularity here. Because if x is 3, there is a singular little problem here. Now, the problem is that the estimate is minus 0.5. Now, suppose I did Taylor Swift, I got this. I see 1 plus 1 over 3, this and that. I calculate it here. It's important for me to reconstruct this back. To reconstruct it, I need two things. I need to know my singularity is 3, and I need to know my exponent, and I can construct it back. Using the method I mentioned before, you see what happened. Doing that, this is what I got. Using that, both differential apportionment and multiplier apportionment, you got this result back. See, for 9 times of the summation, better apportionment, you get this accurately. That really is equality. Then I increase it to what I always do Taylor series, take it to 12, take the coefficient, put it inside the method I showed. I got 3 to 3. So from 9 times, the result of that, I was able to get my equality. What was the exponent? Minus 0.5. I can write this over. Using that method. Now, let's go to general functions. Then I now take functions that have algebraic singularity. Function that has essential singularity. Function that has arithmetic singularity. I put them in Taylor series method. Let my test on, and you see here, you have singularity as x equals to 3, x equals to minus 2, you have it here, and the exponent here, you see it all will be 1 over minus 1 over 4. And this one, in this half, you take it off, you have the singularity minus 1. So, we were able to get all these important property of this and construct it back. And the solution for different kinds of singularity in the system, we were able to get some reasonable results. These are results we get. So, example 1, you can get exact. For this, we were able to, for example 1, we were able to obtain all their singularity and everything. There was a paper I published where I put all those things in. Now, what you know is working. Let's now go to engineering problems. Now, let's the application is that accurate solution of higher non-linear differential equation, modern unit system and so. That's the application. But to do it, you must get your partial solve. Looking at the problem, you must be able to get the partial solve from that problem before you start applying the method. So, and when you do that, you can now analyze the solution and get the, some information about the dynamics of the problem. So, okay, now, let's go into modeling. When you model problems, I always mention there are steps to take in engineering or science. You have your physical problem, if it's a biological problem, if it's an engineering problem, environmental problem, and so on, it's a physical problem. You can turn problems to mathematical problems by making reasonable assumptions, and the guys don't give reasonable assumptions, apply physical law, because everything is governed by physical law. Apply physical law that governs the system, that will have knowledge of the problem you want to model. Then, you will get the differential equation, NFPD or ODE. Then when you get that, or you can get stochastic differential equation, you will pick up optimization problem and all those things, then with constraints and form of social equation, so you can get all these type of things. Now, from there, apply the same boundary conditions and the results and continue again. So don't consider as valid for that. Now, when you solve problem in engineering science and biology, and being modern, I always mention that you go easy way, don't go complex way. Go easy way this way, don't go this way. If you want to go there problem, make critical assumption, don't pass all the parameters in the problem to start with. Look at what is important, remove others, solve the one you can solve with your, because the more complicated the problem, the more mathematics you need. The more numerical methods approach you need to do to really get important results that can change situations. So you start, when you get the solution, you work up the, rather improve it by adding more armor, and more mathematics is needed, more numerical calculation is needed, more method is needed, then you get there and you are improving so as to get to the top. Now, let me give you some illustration. Look at conservation law. I want to model a problem that deals with fluid dynamics, mechanics. So if you want to model a problem in general fluid mechanics, you must know conservation law. Those are physical laws that govern. Without that, you can't jump into modeling the waves, the airflow, pollution in the air. You want to block in the atmosphere. You want to model issue that deals with nano fluids, cooling system in engineering, and all this involve fluids. Then you need to know this. These are just basic things. They are not the model themselves. They come from the conservation of, for instance, you know the conservation of mass. We talked about mass, the rate of accumulation of mass in the system, the reservoir, what mass in and mass out. Then you know what is accumulated. You get some equation. That conversion of momentum. When your flow is equal, in this case, I assume incompressibility. The density of the fluid is virtually constant, although it doesn't change. And this applies to liquid in both cases. But for gas under high pressure, you have liquid gas, you are still applying to the incompressibility assumption. Other gas dynamics, if it's under high pressure, you have liquid gas. So on liquid hydrogen, all kinds of things, what are still under some approximation still make use of vehicle. Now, the other point you need to take note is conservation of energy. This is not from second law of Newton. That's because when you for the undergraduate student in engineering and apply material, you teach how to derive, how to this and that, and get all these things. And now this one is body force, which is your response. In case you have magnetic field applied, you have J1 negative is magnetic field, and you design field at home, and a single phase flow, you put it in. Now let me ask the question. This connection of energy, this will come from the first law of thermodynamics. Connection of energy. So that one, you have that, and this duality, and you must be able to understand this first before you go to modeling. Non-linear, and if your problem is non-Newtonian, this for Newtonian field, this part will remain the same with convective acceleration and time derivative, with convective derivative for this part. But this part, which is your surface force, the surface force on the system will change. Pressure grade will be there as a normal force, but this physical force will change for non-Newtonian. So all those force, you teach students to know all those basic things. So once you know that, then you can go into modeling. Now, if you include magnetic fields, then one has to go to Maxwell law of electromagnetism. Ask law, because this is your response, which also control the put magnetic field. So all these Maxwell equations to come to Faraday law, which law and so, because you have J and B. So all the results here come from here. You have to, which form your body force anyway. That's body force, and if I have gravity, depending on the geometry of the system. Look at the system, how all these things are configured before you go there. Now, we move forward, because I have a lot to talk and time is running now. So, for the area of what I've been talking about, of using that method, a few problems I did to apply the method done and I confirmed in the literature. These are few of them, and they are just using the same analyte per day. And there are more things you can apply against some reasonable results, like this one, which was published in They apply mathematics and computation using this stability for examining stability, use of stability analysis, get solutions, various solutions, and analyze their thermal stability and so on. And here is microwave solving, we go through thermal per day. Here, when you are starting, when you are doing, at times you do single author, you work alone and so on. When you get to certain stage, you become useless. That's why collaboration is important. Because when you collaborate, and do this one, they get more robust results. Don't be the only one writing code, plotting, analyzing, all of that. Somebody is doing and doing this and that, and they make work very fast, and also make it more robust results. So that's why I always talk about collaboration. There are many problems that you can tackle now with the power of computing and with collaboration, that you can get fantastic results with innovation. So you have that these other problems that I probably over 70 papers that time when I was so excited about better working. You know, when you do something, you think I was working, started trying it and do all that things like that. After the time you relax, you start thinking, what else do I need to do? So now you have all these which are done, you see computer analysis application, the other one, this all this with this application of these methods to tackle problems in various things. It's a very interesting thing to number of ranking institutes and so on. So all these things were done that time, and the next thing we do, I do now is okay, which one for 2017 is a collaborator in Bangladesh, very close to India here, we work together and we look at the issue of diffuser. And when we look at that, we derive the equation, and where we derive from there, using similarity transformation. So we got this. This one comes from the Navier-Stokes equation, where it was from the energy equation. And the parameter involved is the Atman number, the effect of magnetic field number, Francis number, Eckhart number, the divergent carbon, and this has a lot of applications in engineering. When you are doing, even in blood flow, auxiliary blood flow and so on, flow in the divergent geometry and so on. So this, when the fluid flow through that, there is possibility of singularity happening because the flow that is laminar may fall to one side of the channel, it goes out to just spread, some will fall. So there is stability in the flow. At what point is that? What I see, there is what we call flow separation. When there is flow separation at the top here, notice fall down here, or flow separation and that way. So you can have some symmetric flow becoming how do we get all the information from the model? And where it is also involved. So look at that. Another thing I can look at here is the number. Looking at this is not linear. This is not linear. Because I see this side is still free, it's a string function, the derivative of its velocity, and so on. Refer to meter here, with the function of temperature. These are dimensionless in infinity form, and they are doing the flow is steady also here, and is steady. Time dependence not there in this case. So you have all these and this alpha number. Actually, if alpha is 0, the divergent carbon, that means everything is still together. So this is divergent carbon. Now, the alpha is increasing. If you take passes in alpha, which is alpha, you can get a partial sum for this problem. Okay. Now, if you do that, using metal, throw it to metal, generate partial sum, metal will calculate those coefficients for you. Don't write a simple metal program, mathematical program, you generate. So I was able to get in the larger carbon, I was able to get some few times. Also, depending on your memory of your laptop and so on, because all these things is a recursive kind of thing you are generating time. You use 0 order to get first order, not to get second order, and so on. So you have to sort them and sort their coefficients and all those things. So we generate them like that, and we now analyze using the method that I mentioned. So doing that, it's a result to go. Luckily, problem which we did here involves nano food. There was a problem we did earlier before when this one when there's no nano particle there. This file which we have here is the one fraction of nano particle in the base fluid. Assuming the fluid we are talking about the neutronium fluid. Now, if file is 0, that the result of it is the liquid. This one is called Jeffrey Amel flow. Jeffrey Amel flow. Those is mechanical Jeffrey Amel flow. This one Jeffrey Amel flow. Jeffrey Amel flow with this one all the go. And when little nano particle was there, and was able to obtain the data points got this is by and we call it Jeffrey Amel flow. Franklin also look at C2. These are what they got, and this is the exponent. And this is what they got. So what we did is, when phi is 0, these are present studies. This is what these people get. Also 3 decimal place. Here we go to, because of the level of computing nowadays, we are going to 15 decimal places. You compare and compare, you convert, you get that. So we did that. Even the alpha, the divergent angle where this similarity takes place. And this is a turning point. So I will realize that this similarity determine when flow separation happens in the so we do that. Now when nanoparticle is there, when the 4.5, which means you have 5% of nanoparticle, 10%, so you can see the magnetic angle changes, the value changes. And you can see here the value is that means nanoparticle flow separation can occur earlier. Flow separation earlier to write the system than when there's no nanoparticle. So we're able to use that and we look at the solution, geometry, plot the velocity and so on, and we find the velocity is of this form, this velocity here. When you apply magnetic field, you slow down, flatten it, when you apply magnetic field. Slow it down this way, and we're able to also look at different parameters here and plot them against each other and see how a parameter against each other using the same method which I've mentioned. So the scale picture is given. These are the critical points in the system which have as increasing those number. So this at this point there is stability in the system. This is a branch of solution, it's another branch. And which one is stable? Then that's where stability analysis comes in. You have 2 branches of solution. You cannot put also for one problem. One must divide the other to do the stability, and to do that you can do linear stability for solution branch, one branch and another branch. And in most cases, we discover that the lower branch is the solution. The upper branch is just there, it's mathematical solution, but in the physical sense, you don't get there in reality because of the model is not linear. So those are the things we have. This Nusselt number, you can see the Nusselt number increases as increases the Reynolds number. Increase the Reynolds number, the speed of the fluid as increases, the heat transfer rate also increase. And you can see here when there is no nanoparticle, this, when there is nanoparticle 5 and this, you can see increased nanoparticle, you can see difference in the heat transfer rate. So these are the for this problem. You look at another problem, apply the method to not to say to test that any problem you can always generate. Here is another problem. You use this problem is the self-distribution problem, which happens in the sugar industry, when they pack all the bandages and so on, or in the coal industry, coal mine, when they put all the electrics of coal, they dump it somewhere, and after some time, they see a black coal smoke coming out without anybody to this fire because of internal heating. Then you have this. So the point, how do we stop this from happening, or this self-ignition explosion? The system, we work out the model, and we're able to find this non-linear. And this one is reaction time. Here you are having multiple reactions, chain reaction. Then this one is heat loss to the average. This will be a radiation, and then work it out using the same method. This bounce number tells the rate of heat loss. So which means you don't want this, you need to increase the bounce number, the rate of heat. So will find a way. If consumption is released, when calculated you have this problem, and what you obtain, use the method generate series, then apply the method 5 miles per day differential and divide to this, and these are the solutions we obtain. We are able to obtain the critical, we want to obtain the solution here when the ignition will start in the system. So if you want to reduce it, you have to kill your reaction to lower the reaction rate by increasing your bounce number. So we have to calculate this point and how this point can be controlled. So that is right in our control. We also have diffusion branch, we have this primary and secondary diffusion branches. Which also leads to issue of a linear stability analysis, adding value problem. You do adding value problem to know which one of them you can, if you do that, you do the benefit and basic solution, then you perform. Temporal stability, you see that this adding value we obtain for this one, it shows this one shows you adding value because what we put here is the wave here to the sea. So we feel the relative one, if this one combined, we are different member. So it doesn't limit here, it's only to do stability of the two solution branches. So it's involved in the stability and then solution branches involved. We don't have problem. We do that, we're able to get this what was also applied. There's another problem here. This problem deals with the issue of nanofluids in the channel. When you have a channel, in fact, the issue of what you call your coolant, this coolant, you put in the radiator to make sure that the engine works properly and it's not overheating. So what we do here is that we loaded that the coolant is made up of anti-nuclear and water. So we have energy and water and we use silver as our nanoparticle. So we do that and we also see that yes, you can use this, you also have to singularity that involved with the problem. Finally, is the nano volume fraction, here is still place, you are putting across there. Then when you do that, you generate the solution here. So the issue is that you go easy way. Although you have solved the problem using finite elements, finite volume, finite value, depending on the argument you can finite difference, you can even disguise and this and look at the make the special very small and then get some sensible results. But without doing that, you can get results using this approach and still be able to analyze what is going on and compare. And when you get yourself, you can also plot it and analyze it in 2D and so on. So this is what for this problem you generate this. No, the point you will get the partial sum. How you get your partial sum depends on your knowledge now. Look at the system. How can you generate? You can even use homotopy perturbation method for those who are doing homotopy perturbation. You can use homotopy perturbation method to generate space. Or homotopy analysis can give you power series. If there is no parameter there, and now manipulate it to make sure that whatever is there can see. So there are a lot of ways now to do all these kind of things nowadays. So you have that and this application will obtain. And you also compute here you compute the critical ITER number, which is for the situation. If there are a lot of energy together in the system, then you can have all these happening. It's not just a linear process, it's not linear. They look at the solution branches, and that can be with differential approximate, you can get all the singularity. And no, once a parameter available in the system as a critical, it affects all the. If you have the temperature affect the velocity, all the very good will be affected. So there's a blow up, there is blow up everywhere. not only affect the SPO, it affects the culture, conformity that are very, very, very system. So we obtain that, we find there is no like also a turning point because it is time now in literature. I'm finishing now, so we have that, and so we get that, and this and the last thing I say is that what I mentioned, collaboration. Most of the things I was able to do for some time I did to collaboration. In China, I was telling Professor Musa the last 2 weeks I was in China before I decided to associate to do some work there in Saudi, this and that, and we have in Australia and Africa. So academic has improved a lot now. You need to collaborate, network, look at this, put your idea, other people put the idea, then work on a very good problem that can make a big impact. And very, very excellent result. And these are those are the areas you see here, you can supervise students to give you a challenge. So that you need to work. And you collaborate and all those things. These are what collaboration can produce. You can see what you call it, Brazil, in US, in India, there are so many collaborators, in Bangladesh, in Saudi Arabia, Middle East, and also Europe. So you need to make, and when you are doing your work, you will be connected. You see the editorial bunch of journalists who invite you to join, you collaborate, you will be able to put some ideas into what is going on, they give this idea, then you can be doing a lot of great things. And by doing this, you can make a big contribution in your field before you leave the universe. So all these things, you are just doing it as you grow. Like my daddy here was telling me, he's 70, is 79 or 70? So he was telling me the age that time, you can see. So you do your best for the young ones, to develop the young ones. Whatever you do is what you do for the young ones to be able to go with. So these are the aims and objectives right now across the globe in academic. So we need to take academic beyond, and it's achieved through collaboration nowadays. So when we do that, we see that at the end of the day, we are producing students network that will live after you. So that's why I put this. So Africa is open for collaboration. And not only me, across Africa, open for collaboration. And the only hindrances, which I already tell you that you must first work. You can't collaborate with somebody who is doing nothing. First work, and whatever you don't know, ask. Nobody knows everything. When you ask, the person will tell you. You may even know more than that person later. So show interest and this and that. So when you show interest and you are thinking of, you get to greater heights in the academic career. So that is the thing, and we are still open for collaboration across the group. So that is very important. And maybe this is the conclusion of my talk, that this university that control the local behavior of system can be determined through this method. The pre-merit of the procedure is likely to receive solution branches. You can get solution branches. Whenever you don't solve, you get a solution branch. And you can get so many things through by various study. And the numerical result presents presented for the ITER, material approximate analysis, for partial sum, within partial sum, the non-linear model, you can improve mechanics, thermal science, and even the biological problem, physiological problem, not only the action. It's not only disease that is biological problem, but a human problem. The fallopian flow is fallopian tube, and the urinary tract, all kinds of things. Not of people in human body can move it. You can know why, what can we do? What are the similarities? What are the problems that are come? That can come there? The model, they are always not there. The analysis is based on. Thank you very much. I think I stop there. This is the end of the talk.
Now, if anybody has some questions for sir? Mike. so long. If you would have some questions.
Hello, Professor. Thank you. Thank you for your nice presentation. Our university. The presenters consider modern problems. I'm saying that this modern problem. It was burning in the presence of oxygen and nitrogen. That equation was in some specific time. So can you explain what and how it
Can
is
you come closer? Come closer. Yeah,
so your chemical reaction that
Yes,
you have
yes.
presented there,
yes,
it was balanced in some certain time,
yes, yes.
but later was burning in presence of oxygen and nitrogen.
Oxygen and nitrogen.
Yeah, can you explain how it is connected to the modern problem? What is the reason of this?
I understand what you are saying. So what the question you are asking is very important. It's even necessary, it's good for what we are having now, use of hydrogen gas production from electrolytes. Hydrogen and the oxygen, everything from water, nitrogen from oxygen, so one thing I want to mention here is that as applied mathematician, before you model what you are talking about right now, everybody, chemical reaction, isn't it? That take place. Like this one I presented, that form the reaction that take place, and so on. I had to go and study that the physics of that particular problem. I studied the physics of that particular problem by literature, there are a lot of experimental work done, a lot of document. But what's mathematics now? So for you to model anything about nitrogen oxygen reaction, first of all, if you don't want to waste your time, collaborate with a chemist. Somebody in chemistry who specializes in those areas. So that person will tell you if the exothermic reaction, if molecular exercise, what is going on, is it produced or what? They know all, they may not know mathematics, but they do the reaction in the lab, we see it. They have the book, the paper, and all those things. You need to understand the physics. Your knowledge to turn that into mathematics and solve and be able to relate to chemistry that okay, what happened this. So that is why research is now multidisciplinary. Multidisciplinary is research today. So we are trained as applied mathematician, not as a chemist. But most of the problems I did in engineering and so on, even for the nanofluid. I use nanofluid now, nanoparticle for desalination of water, seawater, to produce water, using nanoparticle. I have to go to a laboratory to collaborate. People who are doing normally physics is there, not the chemical engineering is there, who are doing those things. And they told me the story, everything, I put it in mathematics. And they were very happy when I was showing them the graph and everything explaining to them. So, for the question you asked, right now, I may not know the kind of reaction between nitrogen oxygen or splitting them, or hydrogen and splitting them, because that is not why I never do experimental work in my life. So, therefore, you need for this one particular one I know is because I studied it and I went to people to get some information and everything before I do the model. So make your research in university, not for engineering faculty, for people in engineering, chemistry is there. You cannot go to chemistry and say, oh, nitrogen, what kind of, can you write the reaction? Tokyo, they call it stoichiometric ratio or something. They put this one you react, what to give, how many molecule of this, molecule of this, what the reaction, you get, you okay in the lab, you see it producing it, you just ask all those questions from there. Then, when you get out of this, you tell me Because I do thermal science, thermodynamics, I know that very well. And I know fluid mechanics, my area very well. Using those knowledge I have, I can now write the equation. Nitrogen is a gas, is a fluid. Oxygen is a gas, is a fluid. Are you following? So I can get those things and formulate the equation and tell you the reaction that is taking place. It is exothermic, what is exothermic? There is in the Arrhenius reaction, I know the equation for Arrhenius reaction. So I can put all those things and the flow rate and what happened, at what point will there be flame or something, and I tell you all those, or change of color or whatever. So that is how I can give you. So for that kind of question, it's good to ask a chemist. Are you getting me? Like the name process, that is the mathematics part, you can do that.
Yes, is the question? Okay. So now I request Professor Samegan Rose and Professor Siksha Chan on stage with Professor McIntyre. So please.
Please, I'm available for this Sunday. You can interact. Work on so many things.
Now for the next session, yes, Professor Murthy. Introduce Professor Murthy. He is a professor of mathematics department from Inaugural. Research papers published almost around 9200. He has had many PhD scholars. His areas of specialization are non-Newtonian fluid flows, micropolar and coupled phase fluids, and mass and heat transfers. He is already a member of many technical societies like Indian Society of Technical Education, Andhra Pradesh Society of Mathematical Sciences, Indian Society of Theoretical and Applied Mechanics, National Academy of Sciences, Administrative Staff College of India. He has also taken up different responsibilities during his tenure, like Dean Students Welfare, Head of the Mathematics Department. He has served as counselor in CCBU in uniting voyages for the admissions of as program officer at UNICHLA and Andhra Pradesh government program Janmabhoomi for development of rural areas. He is also the editor and reviewer of many of the journals. Request now Professor Murthy to take for the talk.
Sorry.
scholars can follow easily. And the topic of fluid dynamics. I am taking the topic from the basic section. How to formulate a problem and over economics. Subject A, very well-known flow called radial flow. This has been taken by Professor Michele. I am also taking the same topic, vaguely or unknowingly. How this radial flow is formed, this I want to take from the fundamentals. This basic flow, I can very well know from 1932, first tackled by Jeffrey, and in the next year tackled by AMSE. So this flow is called generally Jeffrey Hamel flow. Two plates are there. The two plates are converging. There is at the convergence of these two plates, there is a source or sink. Because of this source, the flow will be coming out from the source and flow in the radial direction along the plates. Then we call it as diverging flow. When there is a sink, the flow will be coming into the sink along the sides. So then we call it as a diverging flow. So the flow is decided by the outflow and inflow because of the sources and the sinks. Here we have to take the proper geometry. The proper geometry for this is cylindrical polar coordinate geometry, because the flows, the plates are given by r is equal to theta is equal to 0 and theta is equal to alpha. And we will take, don't take theta is equal to 0, because we have to take the, whether the flow is symmetric or unsymmetric, we have to decide. Therefore, convenient geometry is to take the initial line along theta is equal to 0, and one plate is taken at theta is equal to minus alpha and theta is equal to plus alpha. This all we will take later. First we will take very simple radial flow. Radial flows are occurring here, very simple geometry. There are two parallel plates of infinite length, and flow is entering through the direction of u, and decide whether these equations are satisfied or not. And then you can see that the other two equations will be automatically satisfied, only the first equation will not satisfy. So this first equation will give you this equation, and second equation along theta direction will give you this equation. Both are involving pressure and the function f. So we have to eliminate pressure and find the function f. Only one equation we will get and decide the flow based on the boundary conditions. So here, to eliminate P, this is differentiated. This equation is differentiated. P is differentiated with respect to r. Here P is differentiated with respect to theta. Therefore, first equation you differentiate with respect to theta. Second equation differentiate with respect to r, and subtract one from the other. P is eliminated, and we will be getting the equation in f. This equation is third order equation. Third order equation in f. And mu by r power r cube is common. Therefore, by cancelling, we will be having a non-dimensional equation like this. We have not non-dimensionalized the equation, but directly we are getting the non-dimensional equation because of theta. So this equation we have to solve. This equation you can solve here. This is the solution we have. A plus b cos 2 theta and c sin 2 theta we have. So this equation you can recast. Cos 2 theta you can write it as 1 minus sin square theta, and this sin 2 theta you can have. This is one independent solution and this is another independent solution. Therefore, integrating C and A will become 0 by using the boundary conditions. Why boundary conditions are like this, we can see here. Here, along this direction, theta is equal to 0. Only we have plates, they are very nearby. Therefore, we have theta is equal to 0 only we have. This plate and this plate are very narrow, and therefore the difference between them, distance is very narrow. Therefore, that distance we can neglect. Therefore, along this direction flow is there, and perpendicular to this direction there is no flow. And volumetric flow rate here, the inflow we have, that we can take another boundary condition. Therefore, using that here, A is equal to 0 and C is equal to 0. And the volumetric flow rate you can measure between the two plates. Therefore, that is another boundary condition, third boundary condition. Therefore, by using the third boundary condition, we have to take the volumetric flow rate. It is known W, let us say. And then we will be having, after differentiating or integrating 3 times, we will have this equation, and this will decide the value of the another constant, and therefore we will be having the velocity finally in terms of like this, and we have pressure equation like this. This will completely decide the first equation you take. The A is adjusted in that. Anywhere this constant will become 0. Whether you take cos square theta, sin square theta, this will become 0. That is a very nice point. I have to, in this form, if you want to say, this cos 2 theta you take, and then decide the value. Then also you will get the value of B. That is a nice point. I have represented in 2 forms, but any form you can take and integrate, and we will be getting in this form. If you take, you have U is in this form and pressure is in this form. Therefore, the solution is obtained directly. And this is the simplest form, the simplest to radial flow. This is from Berger. And then we have another radial flow, another simplest case I am taking. This is flow between 2 parallel plates. The discs are moving up and down. When we put a pressure on the upper disc, this will press the fluid, and fluid cannot go up and down. Therefore, it will go in a radial direction. Therefore, this is the possible way. Therefore, this is another simple way where we can consider radial flow. Here also the same condition. You can take velocity only in the radial direction, not in the other 2 directions. Therefore, velocity is possible in the radial direction. Again, in the same equation as in the previous case, we have U is function of Z, because this is not function of theta. You should not take function of theta. Why? Because this is moving up and down. Plate is moving up and down. Therefore, we have to take the flow f of Z, we have to take. It is not f of theta. This is the way, by seeing the physical nature of the problem, we have to decide. This is what I want to stress. By seeing the boundary conditions and the nature of the flow, how to decide the function. That is important. We are not taking the function here f of theta, but we are taking the function here f of Z, because the flow is not in the upward direction, or flow between the parallel plates. Therefore, flow is changing in Z direction, not in theta direction. It is a symmetrical flow. Therefore, we have this. Previous equation is not symmetric, because from theta direction it is changing. Therefore, you have to decide the value of theta. In this problem, at all values of theta, the solution will be set here, along this direction, along this direction, along this direction. In all directions, at every theta, the solution must be set. Therefore, this is a problem of symmetric flow. Previous equation, previous flow is not like that, because At different theta, the value of solution will be changing. Velocity is changing. Therefore, it is function of theta. It is not function of z. This way we have to decide by nature of the flow how to decide the functions. Then we have to decide the flow as Fz by R. And then we take the equations of motion, and the first equation will give you the radial direction, will give you pressure like this, and then we can integrate this and we can write pressure in this part. And then P1, P2 are the pressures at the inflow and the outflow of the geometry here. We will have it here. Pressure is known at this point and the pressure is known at this point. So at these 2 points we can take, it is exposed to air, we can let us say. Then we have to take pressure as ambient pressure, or we can take ambient pressure as 0. Then we have P1 and P2. If it is not ambient pressure at one point and another point they may be different, then we can take P1 and P2. If it is exposed to ambient pressure, and generally we can take pressure at that point 0. Therefore, we have Fz is decided now like this, and this is function of only R, and this is differentiated with respect to Z 2 times. Therefore, by integrating 2 times, we will be getting a velocity in terms of F in this part. Therefore, mass flow, the flow through the plates by integrating 2 times, we will be getting the mass flow here like this. The required quantities are obtained now. The flow is, the problem is solved like this. Now we will take another situation where we have 2 cylinders. These cylinders are here, flow is entering from this cylinder into the outer cylinder radially. This is the case, let us say. Then again, along z direction, they are infinitely long plate, let us say. Therefore, flow is symmetric about theta. At all points of theta, flow is same. Therefore, at every point along z direction, the flow will be different. Or this is also very long flow, infinite length. Therefore, at every point of z also, the flow is symmetric, let us say. Therefore, flow is same at all cross sections of Z, and flow is same symmetrically entering into the cylinders. Therefore, at every theta, the flow is same. Therefore, it cannot be depending on theta and it cannot be depending on Z also. This is the situation. Therefore, in such case, there is no Fz, no F theta. Therefore, it must be a constant. Therefore, U is C by R we take. Then the equations for velocity we have written, and this is only function of R. P is function of R. It is not depending on theta and Z, and therefore directly we are getting the pressure equation. And C we can decide from the which condition we have to take for velocity. This is important now. Here the flow velocity here is not same, here is not same, but it will be depending on only the volumetric flow rate. The flow rate through these cylinders must be constant. Therefore, volumetric flow rate will decide the constant C. Therefore, there is no boundary condition at outer cylinder or inner cylinder. Therefore, the flow boundary condition is through volumetric flow rate. Therefore, by using the volumetric flow rate, this value of C can be decided. Then we will take up another example. Radial flow through a porous medium. Here we are taking previous cylinder is same, flow here. Here 2 cylinders are there, flow is entering here and passing through this. Therefore, but the medium here is porous medium. Therefore, the constant C will be affected. How it is affected? So here porous medium, what is the nature of the porous medium? How it can be modeled? it can be modeled by a Darcy equation. So grad P is equal to mu by K, Q bar we have. Therefore, del square divergence Q is equal to 0 for incompressible flow. Therefore, del square P must be 0. If we solve this, we will be getting P, and here pressure we can obtain like this. At the lower upper cylinder and lower inner cylinder and outer cylinders, P1, P2 are the pressures, let us say, and therefore pressure is given by this equation like this, and substituting the grad P is equal to U, and then we will be obtaining the velocity equation. And by taking the integration 3 times, we will be getting the volumetric flow rate through the cylinder. The problem geometry is same in the previous case and in this case, but the flow is changing according to the Darcy's law. Therefore, to determine the constant, we have to use the Darcy's law. The problem is same, but here nature changes because of the pattern of Darcy's law. So, this is one way we can take. This is also given in the book bird transportation phenomena. Then we will take another example where radial flow can be occurring. Very simple problems only I am taking. Then we will enter Jafari and Hamilton's flow. Here there is a bubble. We are blowing the bubble. Therefore, fluid is entering in radial direction and the bubble is expanding. Therefore, this is the case where radial flow occurs. When radial flow occurs, we have to take cylindrical coordinate system. Previously we have taken. Therefore, now we cannot take the cylindrical coordinate system because it is a bubble. Source is at the origin and the bubble is expanding in all 3 directions. Therefore, this is a 3-dimensional flow. In 3 dimensions it is expanding, but the flow is, we call it as 1-dimensional flow, because how many quantities of velocity is present, by that we will call it as 1-dimensional or 2-dimensional, 3-dimensional. In spherical coordinate system it is a 1-dimensional flow. Therefore, only in the radial direction flow is there, other directions flow is 0. Therefore, by taking the mass equation, continuity mass equation, U is given by C by R square. Previously in cylindrical coordinate system, U is given by C by R. Now we have C by R square. This is the difference between the polar coordinates and spherical coordinate system. And then volumetric flow rate we know, you use this and velocity can be, C can be obtained and substitute back. Therefore, velocity is known in terms of Q, volumetric flow rate, and the flow is known entirely. U is given by 1 by R square. And using the pressure equation and use the radial flow direction, and then it will give you the pressure, and the pressure is given by this direction. This is another simple situation, and here the problem can be modified. How it is modified? We will take another example. And here, let us say the fluid flow is surface is not constant. It is changing from time to time, and radius is expanding when we are blowing. Therefore, this is the boundary condition. So, this boundary condition, how to we adopt, how to put into the practice? Here, the previous equation we have, U is equal to C by R square. Same equation we have, but the boundary condition is changing. How it is changing? We are blowing, and therefore the surface is expanding at the rate R dot. And therefore, that is given at R capital R is equal to capital R. The velocity U naught is known, let us say, and therefore by this we can obtain the value of C and substitute here, and we will be having the velocity equation. The same problem previously we have and now also we have, but the boundary condition is changing. Therefore, how the problem is changing? This is I want to indicate. So, pressure is obtained like this. Now, we will take Jeffrey flow problem. This is a very well known problem and many researchers have taken, and it is first taken by Jafari in 1932, and immediately 1950, and immediately the next year, Hamel has also taken. They don't know each other, but the papers were published. One is in English, the other one is in French, I think. French or French language it is published. Therefore, the second paper, it is in the French language, we cannot understand. We can understand only the Geoffrey, how he has solved this problem. And here, one plate is at theta is equal to alpha, another plate is at theta is equal to minus alpha. Therefore, angle between the two plates is 2 alpha, and the one plate is here like this, other plate is like this. Flow is here in 3 dimensions. In z direction, flow is at every z cross section, flow is same, let us assume. Therefore, it is independent of z. And flow is depending on value of theta from here to here. The flow is not same. Therefore, you cannot take everywhere theta is same. Flow is same. In that way, we cannot take. Therefore, we take u is equal to function of theta by r. To satisfy the continuity equation, we have to take like this, and then continuity equation is identically satisfied, and then we have to use the momentum equations. And here, this is solution is given at different Reynolds numbers and alpha value by Dennis, by a numerical work. Dennis has given, and here if you take converging channel, this is green area. If you take diverging channel, this is this area. The flow is not same for diverging channel and converging channel. How it is, we will see later. Here, the converging channel we have R is equal to 5000, R is equal to 1342, and R is equal to 50, R is equal to 0 like this. And here R is equal to 0 is the middle line. This is straight line. And we have converging channel, and here diverging channel, how they are taken here. The nature of the flow is completely different for converging channel and for diverging channel. Why it is happening? Long-Lewis explains the meaning. Here, u is function of theta by r we have, and take the radial theta direction velocity momentum equation, and p is given in terms of f of theta and integration constant g of r, and substitute in the radial direction velocity, we have this equation. Now eliminate p gr, then we will have this is function of z and function of theta, and this is function of r. They cannot be same unless and otherwise both are equal to a constant, and this constant we call it as k mu. K mu, why? Because this mu and mu will get cancelled. Therefore, you call it as k mu instead of writing k. Therefore, we have this equation. This equation here, this k, if you replace by k by minus k, because of the presence of nonlinear terms, case f square in the equation, here nonlinear term here f square we have. If k is replaced by minus k, we don't get the same solution because of this nonlinearity present here. Therefore, for converging channel and diverging channel, it is different flow curves we have. And if this term is 0, what happens? So the conclusion must be, if k is replaced by minus k, converging channel and diverging channel must be reversible. So such flow we call it as reverse. Flow is reversible. Flow is reversible means it doesn't mean that the just like in the chemical reaction reversible. This is not the meaning. If you reverse the boundary condition, flow reversal you can observe. That is the meaning of the flow is reversible. Here, because of this nonlinear term, we have this. This is explained by Langlass, flow viscous flow by Langlass. You can observe this meaning. Why K is taking important place here. Then the previous equation, third order equation, you can convert into first order differential equation by multiplying the first equation by f dot and integrating. We will be getting this solution, this equation. This equation is a third order equation in f. So this third order equation you can factorize and you can call it as f minus f1, f minus f2, f minus f3 and f dot square we have, and this we can put into the this is function of f and differentiated with respect to theta. Therefore this we can convert into integral equation like this, and this can have a solution in terms of elliptic functions, Sn function and Cn function and Dn functions. So how we can convert into elliptic functions is given here by Dennis. Here, this f dot square we can write because it is cubic equation in this part, and there is a restriction here by observing comparing the equations, this equation and the previous equation. We can observe that f1 plus f2 plus f3 is equal to minus 6q. You can choose f1, f2, f3 such that they are increasing order, and then put this substitution in the above equation, and you can recognize that this is in this part. d phi by d whole square is given by 1 minus k naught square sin square phi, and this is nothing but after integration you can see that it is a elliptic function in Sn. So the solution is given by elliptic function Sn, sin elliptic function. So the solution is known completely. Now special case. Here if you take f2 is equal to 0, that will correspond to the physical situation where maximum flow is occurring along theta direction, and therefore this is a physical situation where special attention is required. This situation is tackled by Dennis, and for different values of alpha and different values of k naught he has tabulated and he has obtained a solution here. By taking all these values, he has drawn the curves. Those curves I have shown you earlier. I am not taking all mathematical formulas what he has taken. It is very complicated and will take much time. We are not interested in it. Then we take another situation where radial flow is occurring. This is conical flow. There is a cone, flow is entering at the vertex and it is a sink or source. Therefore here again we have to take spherical coordinate system, and u is given by f theta by r square. Here we don't take z. It is at all cross sections the flow is the same, let us assume. Therefore it is independent of z, and we have phi. We are taking r theta phi. Therefore at all cross sections phi is equal to constant, the flow is same. So if phi is equal to constant means along this line, along this line, along this line, flow is same. That means phi is equal to constant will not affect the flow. Therefore we have to choose only function of theta. Therefore u is function of theta by r square we have substitute in the previous equation, and we can have a solution like this. And here also you have to decide the constant. This is cot theta. Here in this part we have the differential equation. Therefore best way is to put cos theta is equal to x and convert to this equation into second order well-known equation. This is a legendary equation, and therefore solution is given in terms of a into cos 2 theta minus cos 2 alpha to satisfy the boundary condition. Theta is equal to plus or minus alpha. We should get f zeta is equal to 0. Therefore by using that boundary condition we have this, and a can be decided by taking the volumetric flow rate, and therefore constant a is obtained and therefore pressure is obtained. And here the problem is extended by Tanner. How he has extended? Now from here onwards the mathematical complication becomes very difficult, and we have to scrupulously examine the situations. Only Jafari flow we are examining, that is radial flow. The first problem what we have taken, that problem is examined, whether the flow is fitting into a non-Newtonian flow or not. That is the aim of the Tanner. So he has taken the same Jafari flow, and by Truesdale has given one important conclusion, one important observation. That is, the coefficients in the non-constitutive equations, they are bounded by this relation, I1, I2, I3. All coefficients, if you take a constitutive equation, whatever coefficients you are having, those coefficients will follow the functions of I1, I2, I3. They are invariants of the velocity gradient, or we call deformation tensor. Therefore, the I1, I2, I3 are invariants of the deformation tensor. Therefore, I1 is given by trace B, and I2 is given by this second principal normal, and I3 is given by determinant of the coefficient of deformation tensor. So, therefore, I1 is equal to 0. You can see this is from the incompressibility condition, and I2 is given in terms of gamma dot square by 4. For most of the flows, for slow flows, it is observable experimentally that I2 is 0, but I2 need not be 0, and I3 cannot be 0. If I3 is also 0, there is no flow. I1 is 0, I2 is 0, I3 is 0. Therefore, I3 cannot be 0. Therefore, I1 by I2, this I2 by I3 will decide the measure how the fluid is having a non-dimensional flow. This parameter will decide whether the flow is non-dimensional or not. So, therefore, this differential, this coefficient will decide, if you are taking the power law of fluid, the actual law governed by the flow, that this coefficient will decide. Therefore, for the radial flow, Jafari flow only we are examining. In flow through core we have taken, and this is the deformation tensor, and I2 is given by this, I3 is given by this. Therefore, mu, if you take this assumption, this is given by this equation in terms of F, and n is not known. Therefore, n we have to decide, and the function F we have to decide. Therefore, mu is given by this equation, and finally we are having a differential equation like this in terms of theta, and F we have to decide. Therefore, this equation we cannot solve easily, and therefore we have to do only the numerical technique. By using the numerical technique, Dennis has arrived the conclusions. Here, theta he has taken, and F he has taken. We have to decide the unknown vector mu and the function F. Therefore, on the same scale, mu is taken and F is taken here. And this is the equations for mu. These are the curves for F, and therefore we have a situation like this. This is one problem where we can examine the Jafari-Hamel flow, radial flow in deep. And here Langlois explains the meaning for eddies. And if you take the coefficients here, whatever parameters are occurring, mu is given by this, and volumetric flow rate is given by this, rho is given by this. No combination of this will give you a length parameter. Therefore, in cylindrical coordinate system, you cannot explain eddies. But if you take the spherical coordinate system, Q is not this. Q is LQ by T minus 1. Therefore, finally, Q star rho by U is of dimensions of L. Therefore, this will explain the eddies. Therefore, in spherical coordinate system, eddies can be explained neatly. Whereas, in the cylindrical coordinate system, the eddies occurring in the flow due to perturbations cannot be explained so easily. And Dennis has covered this, and he has explored that. I am not giving you all that. And Rosalind later he has taken the equations, and we have previously the solution in terms of sin x, where sin x, sin elliptic functions we have. Here, okay, I will take this and explain here. Here we have the solution is given in terms of sin x or sin theta. That we can write in terms of lambda and capital X, let us say. X we have to decide. If this is set to 0, we will get different values of lambda. If x is in between lambda 1 and lambda 2, the flow will be having here, the flow is having only one outflow. If lambda 1 and lambda 2 are occurring, theta lambda alpha is in between lambda 1 and lambda 2, you can expect one inflow here, one outflow here. If you theta is in between alpha is in between lambda 1, lambda 2, lambda 3, then you can expect outflow here, three times, and inflow here. If lambda is having values 5, therefore alpha is in between lambda 5, and then you can have inflows under this. In this way you can judge the flow, how it is happening. And similarly this is for converging flow, diverging flow, and similarly for diverging flow. I will start with the next session is ready to, I will complete it. And then we have taken this, and then there is a very good work by Frankel. Sir has shown in the tabulated form how Frankel has obtained the results and his results. Both are compared in this table. The same problem I am taking. Here this is the differential equation, and we have to take string function in terms of g, let us say, and function of y is taken by theta by lambda alpha, and we will be having a fourth order differential equation, and boundary conditions are this solved, and then the previous work and this work, how it is different. Here in the previous work Jafari and others they have not taken non-dimensional equations. This equation is taken in the dimensional form itself, and they have found the solution. And here Frankel has done non-dimensionalization. So the non-dimensionalization, what is the effect? We is getting here alpha and Reynolds number. In the previous equations, alpha and Reynolds number are not there. Only boundary conditions are involving alpha. So through boundary conditions, only alpha is involved. Now, by taking the non-dimensionalization, what is the advantage? The alpha parameter is coming into the differential equation instead of boundary condition. This is the advantage. Because of this advantage, Frankel has so much of observation and has taken regions of flow. He has decided what are the regions of flow for different values of alpha and r. And one more observation we can take. Here alpha square is positive. Here alpha and Re is product is observed. Therefore, here Re and alpha, if product is negative, we have one type of flow. If product is negative, we have another type of flow. Therefore, the flow is decided by the sign of Re and alpha. Because this cannot affect the flow. Because alpha plus or minus doesn't matter. Alpha square we have. Therefore, the flow affecting parameter is Re into alpha. So, deciding by Re into alpha, he has categorized the flow into 7 regions or 5 regions, and those are given here. I skip all this, and he has formulated this line. And Dennis has given, I have not extended up to this, I stop it. Dennis later has given a numerical scheme how to solve a famous numerical scheme by central difference scheme, and he has arrived all these parameters what he has has taken by numerical scheme he has obtained, and he has concluded that by properly selecting RV and alpha. This is RV and this is alpha. So the regions of the flow is divided into 5 categories. All categories how we can obtain. So this is my aim. Taking the same problem, boundary conditions are changing, the physics of the problem is changing. How to obtain the solution? This is what I expected to do, and so that it will be scholars can put on the attention on the physics of the problem and decide the solution. Thank you for giving me this opportunity, for the organizers and my friend Ms. Radhi and R.K. Sharma sir. I thank very much for it. And Professor Dasta is very much known to me for many years. I am coming here to see him and the Lord Jagannath. Thank you very much.
Thank you, sir. Anybody with any questions, we'll just give you 2 minutes for the questions. We are already short of time. So I will request now Professor G.C. Das and Professor R.P. Sharma to please felicitate Murthy sir. Thank you very much. Thank you. So this was the last session of this talk, and we have now lunch. After lunch we will meet here for the technical sessions to be continued at 2:30. Since we are delayed by half an hour, so we'll meet half an hour delayed at 2:30 over here for the rest of the technical session. Thank you everyone. Please proceed for the lunch upstairs.
ଛିଡ଼ା ବି ବୋଲି ଆଗେ ଭାବୁଥିଲି ଆପଣ ଗଲେ ମୁଁ ଦେଖିବି ଉଠାଏ
ଏଇଟା ସବୁ ଲଗେଇଦେବା ଦରକାର
ସେଥିପାଇଁ ତ ମୁଁ ଅଳ୍ପ ଘିଅ ଦିଅ ବୋଲି ଘରେ ଆପଣ ରଖୁଦେବି ନାଇଁ ମ୍ୟାଡ଼ାମ୍ ଆପଣ ଯାଆନ୍ତୁ ହଁ ବାସ୍ ଆପଣ ଉଠିଦେଲେ ଆମେ ଯିବୁ ଠିକ୍ ହେଇଛି ପାଖକୁ ଯାଆନ୍ତୁ ଜଗନ୍ନାଥ ଟିକେ ଦୂରେ ଯାଆନ୍ତୁ ଏମିତି ଆଉ ଗୋଟେ ମ୍ୟାଡ଼ାମ୍ ଆପଣ ଏପଟେ ନା ଆପଣଙ୍କ ସେତେବେଳେ ହେଇଥିଲା ମୋର ଗୋଟେ ସିଙ୍ଗଲ ଲୋକ କେଉଁ ପଟେ ବୁଝିଲେ ଏପଟେ ନା ଏପଟେ ଭଲ କରୁଛି ହଁ ଭଲ କରୁଛି ଏଇଟା ଗୋଟେ ହେବ
Yeah, I think they yes, she said.
Hello, sir. Thank you.
इंटरनेशनल फिल्म का भी नहीं बना देखो ये दिन थोड़ा एक ब्रेक चलती तो ब्रेक रखी तो सेटिंग या सिस्टम सेटिंग को सही लगे से जो सेटिंग सिस्टम लेकिन जैसे कि देखो अपन जहाँ चीज पर रिफ्लेक्शन हो जो ऊपर नीचे लगा दो
एक फोटो ऐसे ही है देखा उसमें लाइट ऐसा
मैंने सही थी कैमरा लगी जा और उसे थिएटर में एक्चुअली बावली का ठीक है फोटो ब्रेक प्रॉपर्ली ऐसे कैप्चर करे और फॉरवर्ड लगी थी से बटन स्कैनर
हां मुझे ऐसे ऐसे ना मैं देखा बस ऐसे ही
आपको कैमरा पूजा कर सिंगाई को समुद्र एनालिसिस देखो
ना कैमरा लेती है लेकिन दे वो लोगों को दसों डॉलर दिखा दो
हां ठीक है किंतु डिले चलती
हां सही छोटा कैमरा सही भी दूर रखिए
हां ये तो बोले अपन लेट के
सेट आसला ପରେ
ଆପଣ actually ଏତିକି ଦେଖନ୍ତୁ ଏଇ view ରେ ଦେଖିଆ ହବ ଏଇ view ରେ ଆପଣ ମାନେ ଯେମିତି ଗୋଟେ ଲୋକ ପ୍ରେଜେଣ୍ଟ ଦଉଛି ସେଇ view ରେ ରହିବ ନା ପୁରା ଯେତିକି view ତାଙ୍କୁ ଦରକାର ସେଇ view ରେ ରହିବ ଆଉ ବାକି ଏ view ଟା ଦେଖିଲେ କୋଣ କିଏ ଗୋଟେ ମୋବାଇଲ ଚଳଉଛୁ କଣ ଚଳଉଛୁ ଏଟା ଠିକ ନାହିଁ ଠିକ ଆମ ସେସନ ଟା ଇଣ୍ଟରନ୍ୟାସନାଲ ଲୋକ ବାହାର ଦେଖିବେ ଦଶ ମାନେ ଏଟା ବ୍ରେକ୍ ଚାଲିଛି ବ୍ରେକ୍ କରେ କିଛି ଅସୁବିଧା बाकी डन जितनी की दरकार सेतिकी दिया
See the email about your postponement. What is the meaning now? Because you will anymore now. No, wait. No, wait for water for the house. Then after put on adrenaline before. Now that means when I'm over I cannot. No, not at all. Initially was already. Oh no, he will only attend yours first. And why the room didn't talk to you first? Tell me the room why I changed as a brother first. What are they doing to these people? They are confusing. Yeah? Hey! No, anything for that. Anything for that. I'll come back to you. Yeah. Sure. Anything for that. I just see the email about the chief's one. So, Dr. Munama could not attend the first session. Oh, because I saw also the review board is pushed to the right. It is going to start at half past 2. Yeah, because if it's changed, for half past 2, then by half past 2 chief will be finished. Yeah, I think we must just continue with the must just finish. Because the big change is half past 2. So that means or they are trying to manage it. They saw that chiefs postponed, then they try to push the review board so that they can make it. I think that's what they're trying to do. can speak to him again and suggest that, because the dean wanted it to be finished by today, which is one. That's what the dean's want. I can just check with them. Maybe there is a reason why we must do that they are looking for to have us to maybe to accommodate this kind of thing. Can check with you. I think it's for the reason. Yes. You see, they are confusing us. Sure. How was the PT or the state not? Oh, the state game is okay. Because mine is, I'm 2 o'clock. I'm 3 hours, 30 minutes ahead. Yeah. No, everything is tight. Even the expo. Go back. You have one seat in front of you. Try to figure out maybe there's a reason why they should do that. So, yeah, I spoke to him to check the email. Maybe there's a reason why they shifted the report to a past 2 instead of 2. Now, yes, there's an email from people shifted to the right. Oh no, I was suggesting for tomorrow. No, we're not checking the Monama because the people just shifted to the right. Maybe you are going to. And we who had a good suggestion. You wanted to start with the man. Oh. Yeah. No, when I didn't get you, when I didn't get it. Commandant's I didn't send anything to PT. I didn't send anything to Siksha. Hey, that's why I said that. I'm sure all others from the chief HR or not, they include now I just said yeah, somebody like Google guidance in us. Oh, I know the voice, yes. But I'm
वो कैमरा शायद लगा रहे हैं
वहाँ चल रहा होगा लाइव ऑनलाइन अभी तुरंत आपका है
3:10 का है
और जब आएगा तब डाल देना अभी तो लंच का टाइम कितने बजे तक कि टाइम पहले ये था एक्चुअली तो आपका
सेशन चल रहा तो वो खुद नहीं करवा काम निकाला
आज इनके पास स्लॉट खाली नहीं हो रहा, कोई नहीं, कोई जल्दी करा देते हैं।
प्लीज सर जल्दी आपका कहाँ जाएंगे कब जाएंगे?
जब हमको लगेगा फ्री है।
हाँ तो सर सेशन चेयर में भी है
नहीं वो तो करना है,
वो कदम हो जाते 6 बजे 6-7
उसके बाद प्लान
उसके बाद
नहीं
परसों का परसों है ना,
आपका परसों है कल तो सर आप नहीं कुछ कल तो
चलो तो कल
परसों का सर कल सारा ऑनलाइन है तो
अच्छा ठीक है। बाकी 2 दिन है। फोन कर रहा हूँ ग्रुप में उनको आइडिया लेता है सांची का यहाँ का है देखो मुख्य दो है एक पूरी और एक बाकी तो एक दिन आप तो बात के थे नेक्स्ट हुआ मतलब जिस दिन समाप्त
Professor Samiran Bose, then next Dr. Bangkok Chandra Madal, and then Professor Anita Kumar. These three speakers, and then Professor Bangkok and
Good afternoon everyone, welcome for the next technical session. Now this session will be chaired by Professor McKinley, and the first speaker of this session is Professor Samiran Bose. He is a professor from Department of Applied Mathematics, University of Calcutta. His specialization is in plasma dynamics and nonlinear dynamics. He has research interest in nonlinear wave process in plasmas and complex plasmas, nonlinear dynamics and stochastic processes. He also has guided a number of research scholars and also published 100+ publications in reputed international journals. He has a few membership in life memberships in some of the societies: Plasma Science Society of India, Indian Association of Cultivation of Science, Calcutta Mathematical Society, Institute of Theoretical Physics, and Advanced Center of Nonlinear and Complex Phenomena. He is also a referee and reviewer of many of the journals. He has attended a number of invited lectures and has research collaborations with many of the countries and universities like Max Planck Institute of Germany, Ruhr University, Bochum, Germany, University of Western Cape, Cape Town, South Africa, and also from Brazil. And his national collaborators are Saha Institute of Nuclear Physics, Kolkata, Indian Statistical Institute, Kolkata, Institute for Plasma Research, Gujarat, Jadavpur University, Kolkata, West Bengal State University, Barasat, and Gorbanga University from Malda. Let's welcome Professor Samiran Bose for his lecture.
So, good afternoon everybody. After a heavy lunch, everyone is tired. So, I will not take that much of time. My topic is little bit different in the sense related to somehow physics. Maybe some applied mathematics are very much related to physical problem. So one of that kind of is plasma physics. So in my today's lecture, I will discuss some phenomena, rather observed phenomena in auroral region. In our atmosphere, auroral region is known as means some rather I can call it a plasma region. One of the most example of our plasma region is the auroral in our magnetosphere, especially auroral region. In that region, different satellite observations showed such type of modes, ion cyclotron mode. Basically, in plasma, in absence of, if we consider two components, means electron and ion, none other than other component, then in case of in absence of magnetic field, there are two types of modes, OM modes. high and low. High is related to electron oscillation and low is related to ion due to their mass difference. As ion mass is very high, so low frequency response is important. But in presence of magnetic field, there are also several modes. Here we consider a particular mode, we call it ion cyclotron mode. And the solitary wave, I think it is very much well known to fluid people also. In case of water waves, in case of ocean dynamics, even in case of medical science, some solitary like pulse are usually observed, like our heartbeat. So this is kind of wave related to nonlinear phenomena. So basically this wave is nothing but a localized structure. Localization means energy localization. Wave propagation is nothing but transport of energy from one to other, or rather transportation of energy, variation of energy with respect to space and time. So solitary wave is kind of nonlinear wave which has some special characters. Kind of it is more stable. If we interact two solitary waves, then they will intact their identity. So that means energy is conserved. So with this, my content is introduction basically my motivation, then description of model, basic equation, then kind of special kind of trapped electron distribution, linear and non-linear mode, and its solution, and summary means its application, rather the observation, how our result explain the observed phenomena in auroral region. So usually it is a very much low frequency wave and longitudinal oscillation, as we already mentioned the word electrostatic. So it's a longitudinal oscillation and related to ion motion in presence of magnetic field, but the motion is not perfectly perpendicular. In case of electron and plasma, in presence of magnetic field, forget about the plasma, in presence of electron and ion, if we put a external static magnetic field, then what happens? Both electron and ion gyrate in absence of other effects. It's the ideal case, both gyrates, and the direction of gyrations of both the particles are different. So in this case, if the geometry is like perfectly perpendicular, if we consider this is Z, this is X, and this is Y, and if the wave is perfectly perpendicular, propagate in perpendicular direction, if we assume the electron will proceeding in the Z direction, and that phenomena will prevent to create wave nature of ionospheric wave, but wave nature of ions, rather low frequency. So the geometry is like that. Almost perpendicular means the magnetic field and the direction of the wave vector is very low, below 4 degree. So it has been experimentally observed. So that's why is a magnetized plasma propagating nearly perpendicular to the magnetic field, and experimentally this wave is observed, but we are considering here only the astrophysical observation. These satellites shows the existence of electrostatic ion cyclotron wave in auroral magnetosphere, and in this observation one kind of electron hole has also been observed, and these electron holes is the signature of trapping of electrons. Hole in phase hole forms if in reality there is a trap, there is a possibility of trapping of electrons. So our aim is to study the nonlinear structure of electrocyclotron wave, electrostatic obviously, in presence of trapped electrons. This is our motto, and after we will discuss later. This is our motto, to study this. Here we present the theoretical and computational studies on the weak nonlinear transport properties of electrostatic ion cyclotron wave in presence of trapped electrons. As we have we already mentioned that in case of ion cyclotron wave, the propagation wave vector is almost perpendicular but not exactly perpendicular. So in our case we consider magnetic field is the Z direction and we consider the perturbation is in the XZ direction. And these are the why we consider this type of assumption. If we consider this type of assumption, then electric field is effectively in X direction, because we are considering longitudinal. So curl E is equals to 0, and so E is equals to minus grad phi. So phi is the electrostatic potential, and considering this, this is the explanation. What we have already explained, 90 degree, it is essential. Some deviation should be there from the perfect 90 degree. Otherwise, no wave exists. In that case, we get only the oscillations. And another thing that in case of usual plasma, in absence of plasma, characteristics, there are characteristics, some characteristics things are there. One is the plasma frequency, another is the Debye length, which is known as the characteristic length of a plasma. In case of plasma frequency related to ion, it is called the ion plasma frequency, and the related to electron, it is called the electron plasma frequency. If we put an external magnetic field static, then another frequency, characteristic frequency arises. That is called the cyclotron frequency. Again, in case of ion, it is ion cyclotron, and in case of electron, it is electron cyclotron. And another two length scale is also arises. One is the gyro radius, because I have already told that in absence of any other effects, if we put in presence of external magnetic field, both electron and ion gyrates. So another scale is has been introduced, that is the gyro radius scale. So in case of ion cyclotron wave in auroral region satisfies this relation. The ratio of cyclotron frequency and ion oscillation frequency is too much less than 1, and which is greater than electron. It is obvious, because cyclotron frequency mass is in the denominator. So mass low, frequency is high. Mass high, frequency is low. So in that sense, it is obvious. But interestingly, when we measure it in terms of length scale, then electron gyro radius is too much less than the characteristic length of plasma, means lambda d, and which is too much less than the ion acoustic gyro radius. So this suggests us that for this problem, we cannot treat electron as fluid. We can treat ions only as fluid. So we have to treat electron as kinetically we have to treat it. Kinetically means there are two types of formalism in case of plasma. One is the kinetic, another is the fluid approximation. In case of kinetic, when particle nature is important, then we have to consider the kinetic approach, or otherwise usual fluid flow. So here we cannot, due to this restriction, we cannot consider electrons as fluid. So we consider electron as we treat electrons kinetically. And for this, first we consider the ion fluid equations. All are normalized. Usual ion continuity equation 1D. And our geometry is like that. In the z direction, magnetic field is z direction. In x direction, wave is propagating. And this the 3 and 4 equations are coming from usual momentum conservation equation, considering the Lorentz force, and that gives us two components, x component and y component part. And this is the usual Poisson equation, charge balancing equation. And so all these are the ion fluid, usual ion fluid equation. This type of equation has already been considered in 1979. All these are normalized quantity, because we are in the ion scale. So with respect to ion scales, electrons always maintain the thermodynamic equilibrium. Next, we consider electron, as we have seen that for this problem we cannot consider electron as a fluid. So for kinetic treatment, we consider the well-known Blasov equation. And in this Blasov equation, we neglect the time part, because as we are in ion time scale, so we cannot perfectly identify the motion of the electron, which is so fast with respect to ion. So due to this is nothing but like a PD of a mathematical problem, and the general solution is like this: F is equals to function of both, any function of phi and v will satisfy this equation. Most of the cases, the solution considered as the Maxwell-Boltzmann equation. That is also a combination of velocity, energy, means in terms of energy, velocity and potential. But here, as the electrons holes are observed in the auroral region, and that represents the trapping of electron, so we cannot consider the usual Maxwell-Boltzmann equation. So for this, we consider the famous Samuel equation, who first gave to explain the electron hole phenomena in auroral region. Professor Samuel first introduced a distribution function of electron, which is famous, which is known as Samuel distribution, and that clearly explained the trapping phenomena of electron. So keeping in mind, we consider the Samuel distribution. This is the trapping electron distribution. And as we know, the fluid equations are, in case of usual fluid, we get the fluid basic equation taking the moment of the kinetic equation. So taking the moment of the first moment of the distribution 7, we get the first electron density, and this is the special type of electron density. And this B term, that means B is equals to 1 minus beta by root pi. This beta factor represents the fraction of trapping electron in the system. If we put beta is equals to 0, we get the usual Maxwell-Boltzmann distribution. But if beta is positive, then we get flat top distribution. But if beta is less than 0, then we get the trapped electron distribution, which explains the whole phenomena in auroral region. This is the linear dispersion relation. If we linearize the basic equation and take the dynamical variables, some kind of cosine or sine perturbation, then we get this dispersion relation. But we are interested in the nonlinear relation. First, if we look at the basic equation 3 and 4, some omega, capital omega part is there, which measures the ratio of ion cyclotron frequency to ion oscillation frequency. So to introduce this effect in the nonlinear regime, we have to scale in terms of perturbation this factor. So for this, we calculate the value of this factor using this data for auroral data, and have seen that omega is of the order of 0.3. This is the maximum value, taking the maximum magnetic field. This is the maximum value. So this value justifies the scaling of capital omega factor, which is of the order of root epsilon. Here epsilon is the perturbation factor. Using this, we finally get a new type of equation. It is new in the sense that it is in the sense of plasma physics literature, this equation is novel. And if we drop the epsilon, means the capital epsilon term, and integrate it, then we get the usual Samuel equation. Those who are very much related to plasma physics problem, Samuel equation is well known. But due to this term, capital epsilon term, we cannot say this is a purely Samuel equation. Because if we integrate it, the right hand side term gives us a non-local term. Because there is the integral term. So we call this equation Samuel-Ostrovsky, because in case of ocean waves, L.A. Ostrovsky first introduced such type of equation with where the nonlinear term is psi to the power half. In that case, it was simple psi, because actually that equation was nothing but the derivative of KdV equation. But in that case, here, this is nothing but the derivative of Samuel equation. So we call it Ostrowski-Samuel equation. And this equation, if we look this equation, first we calculate the energy of this equation by multiplying psi of both sides, and finally we get this. And here the epsilon rod, this part is comes due to the presence of Lorentz force, due to the presence of magnetic field. And if we look the plasma system as a whole, then energy is conserved. But if we look the weight as a single identity, then in that case there the term is like that del energy E tau is equals to minus E d tau, means with time it decays. And and the last one, if we put what we have already told, if we put epsilon equals to 0, then equation is quasi-integrable in terms of integrability. So our first aim is to solve this novel equation analytically, but the characteristics which can tell, which tells us that this equation is exactly integrable. Using this character, we observe that this equation is not in that sense exactly integrable. Means we cannot find any exact solution of this equation. So again, we have to try some perturbative technique, well-known perturbative technique. And this technique is KVM method, means Krylov-Bogoliubov-Mikhtuvsky method, and one can finally get this result if someone use the energy integral method. But instead of that method, here we use Krylov-Bogoliubov-Mikhtuvsky method. And the motto of this method is, first we forget about the Samuel-Ostrowski equation, we consider the Samuel equation, and Samuel equation is exactly integrable. We know the solution of that Samuel equation. We take that solution part as the initial solution of this equation, and using some rigorous mathematics operator theory are there. So I am not giving you all the details, discussing all the details, and finally collecting the epsilon term, we get this type of solution where amplitude n tau is time dependent, width is also time dependent, and if we look the expression of amplitude in equation 17, we will see that at tau is equals to tau critical, the amplitude equals to 0. And in that case, later we will show that because at that tau is equals to tau 1, energy is also 0. So this equation means this solution, but rather if we give a solitary pulse, this solitary pulse will not sustain for over a long time. After a finite time, this solution, this solitary structure will collapse. Now question is that what will happen next? The question is that what will happen next? To see the character of the next part, we numerically simulate this using pseudo-spectral method. All these are usual numerical conditions, means part, and use two initial conditions. The first one is the usual Samuel solution, and the second one is some wave packet solution. We will see later. And these are the parametric value we have used in our simulation, rather in our computation, and all values are taken from the auroral magnetospheric region. This value shows that the tau critical increases with the value of B0, and at the same time with the value of D also, means tapping parameter. And if tapping parameter is large, then tau is large, means the collapse will occur later time. And this is our computational result using sec⁴ initial condition. If we look, you will see that tau equals to 0 was the initial pulse, and when we increase tau equals to 5, tau equals to 7, we will see that the actual solitary, solitary part is decaying and some tail is formed. And all these tau values are less than tau critical. Now, if we again simulate this, we will see this type of structure. All are bounded solution, and we took it. We have already seen that here the plot are shown from minus 200 to 50 because of the clarity of the fixture, but our simulation was from 10,000, minus 10,000 to plus 10,000 we computed. And this picture tells us some wave group nature, means wave packet nature is also there. That means after tau is equals to tau critical, when single solitary wave collapse, then there is a possibility of formation of wave group, rather wave packet. And interestingly, we also calculate the dotted line is the numerical tau critical, means where the wave packet starts, and the blue line is our analytical form. So these are almost same, means our analytical part is correct, rather justified with respect to the numerical results. And these figures we gave, if we instead of the sec to the power 4 profile, if we use the second initial pulse, which is usually taken for the wave packet to study the wave packet dynamics, exponential minus this, sin this, so we get the exactly wave packet phenomena. We show the wave packet phenomena, means wave group dynamics. So from this we can say up to tau critical solitary wave is okay, tau critical it collapses, and then wave group dynamics started. And this wave group dynamics corresponds the spiky structure of electric field. This type of electric field structure has been observed in auroral plasma region. And so our motto was to study the motto was to study on the basis of the observation ion cyclotron wave in auroral magnetosphere in presence of trapped electron. We considered that problem and modeled that problem, and finally we get that spiky structure which has been observed in auroral region. For an illustration purpose, if we take some kind of numerical factors, say electric field is 0.1 and E field is unnormalized, then we get the unnormalized value 10 to the power of 10 to the power 3, which was well agreed with the first satellite observation of the previous result, observational results. So that's all. So we start with a simple model, and finally what we get, this can explain some physical phenomena observed in auroral regions. And this work has been published. If anyone interested can consult with this paper also. And these are my collaborators, rather these are my two students. First one is now doing his postdoc at ITER, Institute for Plasma Research, and the second one is now a teacher in a college. So thank you.
Question. Okay.
So you have shown one analytical, the comparison is analytical result and numerical thing. So which equation, so that analytical result is just for the wave equation or for the sample equation?
The analytical result was a part of the result. Yeah, with epsilon. That's why I am telling. It's a solution. Come. This one. So this part, this is the usual channel solution. Okay, in presence of pattern quantity, means say some we can see better in this form. We just integrate it, and the left hand side is nothing but a simple channel equation, And we took this capital epsilon, which is omega square by 2. This is the Patab quantity. And our numerical table shows the values, we can consider it as Patab. So, considering it as a Patab quantities, we first take the left hand side, means epsilon equals to 0, we get this. And in presence of perturbation, it is an assumption that both amplitude and width and other related parameters are also a slowly varying function of time. So, taking this tau 0 is equals to tau and tau 1 is equals to epsilon tau, and finally we get this. This is the Patab quantity. We consider up to epsilon of the order of psi 0 plus epsilon psi 1. We neglect the of the order of psi square. And here the results, what we have put here, it is the value using epsilon tau is equals to tau 1. Instead of tau 1, here all the results are related, we type it as tau. It is purely, it is called, it is very much in nonlinear PDE, this type of solutions are very much well known. These solutions are called leading order solitary wave solution. And it was Gauss, the famous mathematician, rather I would say mathematical physicist, who first told that in case of any nonlinear kind of equation, KDE or like that, if there is some disturbance of small kind of disturbance, then it would be better if we consider the energy conservation equation, and then we can easily find the leading order. Again, I am telling you the leading order, because other term is there, but that term is of the order of epsilon square. So it is not at all exact.
Any question? My comment also is on what you mentioned, that is that the exact solution?
It is not at all exact. From the very beginning I am telling that it is not at all exact. Because to test the exact solution, Kenlev is there, so many techniques are there, we have tried, but we failed. So it's a real Patab solution, but these solutions serve our purpose, that because the first solution, that part is called the leading solitary wave solution.
Now, any other question? Have you considered the numerical solution of the problem itself instead of perturbation?
We consider it. We have solved this equation numerically. No, not at all first order. Not at all first order. These solutions are purely our derived equation solution. Not at all first order solution.
In the absence of question, can we thank the speaker for excellent presentation and for being able to show us how the military wave based on plasma flow, and yes, can we have a lot of applause for the
Thank you.
The second speaker.
Thank you.
Can you do the
Thank you so much, sir. I request Professor G.C. Das sir to felicitate Professor Ghosh with a memento.
वायरलेस में एक दबाव बोलो सही करना आरड़ा
Thank you, sir. Next speaker is Bankim Chandra Mandal, sir. He is currently working as Associate Professor, School of Basic Sciences, IIT Bhubaneswar. His research areas are numerical analysis, partial differential equation, domain decomposition methods, and scientific computing. He has guided several PhD and MSc scholars. His major achievements are the Best Presentation Award in MPHPCST, which was held in IPEC New Delhi. He also got the Excellence in Teaching Award in IIT Bhubaneswar. He has a number of research publications in reputed international and national journals. I request him to be present here.
Hello. So, thank you Dr. Rakun for the invitation. So, I'll briefly explain what is domain decomposition techniques and its convergence behavior for linear and non-linear partial differential equations. So, since very few people working on this domain decomposition technique is in India, so this talk will mainly on the overview of the methods and how it behaves for different type of problems. So this is my outline of the talk. So I will briefly explain introduce domain decomposition technique, and then their convergence results for different type of problems, and then I will conclude. So this picture is everywhere what I see. This is a very because it is in Orissa, so I think everyone is familiar with this temple. It is a Puri Jagannath temple, and I have a favorite corner in the temple premises, which is the kitchen, the Rasasala, right? And on a daily basis, 56 different types of food offerings are done, cooked for around 20,000 to 50,000 people on a daily basis, right? And there is on an every day there is a specific schedule or routine for the food offering. So the amount of food that is cooked, there has to be cooked in a very quick time. So the total wall time for cooking is very important, and which is very similar in many numerical simulations example, right? And so there are various myths about the cooking procedure of in the temple. So there is one myth that probably everyone heard, that the pots are kept one after the other, and the pot at the top gets cooked first and the bottom one at the end. So basically they say that this cooking is done in sequential manner, rather reverse sequential manner. But if you visit the temple and if you look through the holes in the wall boundary of the kitchen area, you can see that this the ovens are basically triangular set, and 9 pots are kept in each of these oven, triangular set oven, and these are called Dabopatro in Odia. So this pictures and all the facts and pictures are taken from this book by Salini Mahapatra. It's a best-selling book in Amazon. Okay, and so what it is done is it is not in sequential manner, but it is the cooking is done in a parallel manner, simultaneously. So it is a kind of parallel computing inside the temple. So that is the idea, main idea of domain decomposition technique. So instead of solving in a large domain or large spot, you divide the ingredient into smaller pots and you do it simultaneously and in combine. So it's a kind of divide and conquer and combine method, right? So what we do is we take a problem, a partial differential equation, and suppose this is my physical domain, and then we divide them into strips, we solve them smaller problems, we combine them, and we try to get the original solution, right? That's the idea. And in this analogy, the number of ovens is basically the number of computer processors available in the parallel computation. So this is one of the method of domain recognition technique, and my name is attached to this discovery of this method. So that's why I am presenting this in a sequential manner, like in step by step, and then we'll show how it works, and it's an analytical technique. So suppose I want to solve a linear problem, wave equation in this physical domain. So the 2 dimensional in space, 1 in time. So this is whole domain. So what we do is first we divide the domain, instead of solving in the whole omega, we divide the domain into 2 subdomains in this case, but you can also do extend it for multiple subdomains. So divide in omega 1, omega 2. So while dividing in this omega 1, omega 2, what we do is we create one artificial boundary or interface where no data is given. There is no data on this artificial boundary. So how do you solve it? So we have omega 1 and omega 2. The situation is the same, but we do not have any data on the artificial boundary. So we take a initial guess or the Dirichlet trace along this purple color interface, and we solve omega 1 and omega 2 Dirichlet subproblem. So it's a Dirichlet boundary on this in the interface. We solve in omega 1, omega 2 in parallel, okay, with 2 processors. We give the data in one processor, another one in the other one, and we do it the computation in parallel, so that you can save time. And because you have started with an initial guess, arbitrary initial guess, the solution is not correct, right? So what we do is we calculate the derivative jump or Neumann jump along the interface and use that Neumann data to solve in omega 1, omega 2 as a Neumann subproblem. So first is a Dirichlet subproblem and then a Neumann subproblem. And then this 3 steps consist of the one iteration. And then to go to the next iteration, we just have to like update our initial guess G. So earlier it was G0, so you have to update that using this linear combination with a parameter theta. So this parameter theta can vary from 0 to 1, any value. And this is so now we are ready for the next iteration, and we iterate until we get the convergence. So this is the Neumann wave from Laplacian method because of this Neumann step. Okay. So what we have observed this is for the simple wave equation, for 2-dimensional wave equation, theta is equal to 1 by 4 is the best parameter, right? And if you take theta is equal to 1 by 4, so for the wave equation, irrespective of like the parameter or anything, irrespective of the mesh size you calculate for the numerical technique, the method converges in finite number of iterations. So if you take, and that is given by this inequality. So if you take t very small, you can get the iteration in two steps. Okay. So this is small numerical test. So this is the wave propagation, wave speed. This is the subdomain size, and this h mean is basically the subdomain length, not the parameter mesh size. So it is independent of the mesh size you take for the finite difference or finite element. And for this like a particular value, you take from this equation inequality that t by n 1 by half. So if you take t, the time window is 2, you will get so n should be greater than equal to 4. So it should get 5-step convergence. So for theta is equal to 1 by 4, theta is equal to 1 by 4, you get 5-step convergence. And other thetas also give convergence, but they are not it cannot be predicted. But for theta is equal to 1 by 4, which is an optimal parameter, you can predict the number of iterations needed. And this is another. So if I vary the time window, the capital what is the time, like the total time is equal to 0.31 and 1 by 4 and 2. So theta is equal to 1 by 4. These are the iterations. So you see that if t is very small, if the time window is small, then you can get it works like a direct method. It's an iterative method, but it works like a 2-step convergence method. So this is a small outline of the proof that you can prove it analytically that in the 2-dimensional in space. So basically, because we are dividing in x, we are not doing anything in y direction. So we can just use the Fourier sine series in y direction, and for each Fourier node n, we can convert into a first like 1D equation with time. And then because it's a time-dependent problem, we can use a Laplace transform in time so that it becomes an ordinary differential equation that can be easily solved. And then using these solutions, you can get the update condition that I show from as in terms of g. So this is a combination of an exponential kernel and the initial guess. And if you get that in the time domain with inverse Laplace transform, So this is a kernel convolved with the initial error. So irrespective of the initial error, if this this kernel decays with iteration number, then you get this becomes 0, right? And it has a property. So this kernel one can verify that this kernel has the property of a Heaviside function. So it is 0 if t is if the quantity is very less than beta, and other than this there is a like a Bessel function comes into the picture. But we are not interested in the second part. The thing is, it gives that for small time window, it gives exactly 0. So it nullifies the initial error. So this is just to see that toy example. So our initial case is suppose this one, this graph. So if I apply that kernel, exponential kernel, it just shifts to the right. So it shifts this function to the right, and until t is equal to 1 value, this value just nullifies. It is just 0. So if we multiply with the initial guess or initial error, it becomes 0. So you get the exact solution. And let me compare with this the method with the well-known Schwarz waveform relaxation method. So this is also a type of domain decomposition technique, but which is little older, which is also established. So there, what we do is we take the whole domain is divided into overlapping subdomains omega 1 and omega 2. So omega 1 has a boundary in the red, and omega 2 has the boundary in blue. And we solve in omega 1, and then as soon as you solve in omega 1, because it's an overlapping domain decomposition method, so in this red one you have used the boundary condition. So while you are solving omega 1, you already have the data on the black one. So you can use that in the omega 2, solving in omega 2. So you can use that in omega 2, and then you just iterate. You just alternate and you can solve it. Okay. So this is called the Schwarz waveform relaxation method, and there is also non-overlapping version is also available with optimized one. So that we have just compared them with our NNWR and DNWR. We will talk about DNWR later. So both these methods were developed in a similar fashion, and we see that this Dirichlet-Neumann waveform relaxation and Neumann-Neumann waveform relaxation methods for optimal parameter, they behave very fast. They converge very faster than the other available methods. Okay. So in terms of numerical efficacy, these methods behave much better. So this is so earlier it was a 2 subdomains, and this is for the 3 subdomains, and the result was similar. So Neumann behaves much better than the other versions. So a comparison with DNWR and NNWR. So this is given by a table. So one dimensional, 2 dimensional, you can also extend it for 3 dimension. So in multiple dimension, this is the results. The conversion results are exactly the same. Only the thing is, if you go from 2 subdomain to multiple subdomain, it takes little bit delayed. So for 2 subdomains, the method converge a little faster. So this is the one numerical efficiency test. So what we did is we take 3 subdomains, and in each of these subdomains we have used different time steps. So this is a quarter time step, this is very fine, and this is the medium. So you can use different numerical techniques in different subdomains. So that is the beauty of this method, and we have used different time wave speed also. So C1, C2 and C3 like this. And time grids also have been given by this is a quarter, this is very fine, and this is the middle one. So we have run this for the 2-dimensional wave equation, and you see that this is basically the time window 0 to 2, and this is the first iteration where there is some error, so you are not getting the smooth solution. And if you do another iteration, it gets converged. Okay. So in 2 iterations, you are getting convergence. So now, so far we are discussing about the linear problem. Now the similar all these methods will apply for nonlinear problems. So this is a cantilever equation, which is a prototype to describe the evolution of melted alloy in under critical temperature, below critical temperature. So the thing is, this is first order in time, but it is fourth order in space, and as well as there is a nonlinear term, right? So epsilon is the parameter which describes the physical property of the melted alloy, And the solution of this cantilever equation also follows energy minimization. So over time, the energy gets minimized and the mass should be conserved. So whatever numerical technique we should develop, they should follow this to physical phenomena, right? And there are many applications to this cantilever equation. You can see that there are many. There is one version cantilever. There is a Allen-Kern equation. So both of them can be solved using this domain decomposition technique. So the applications involve the biophysics, planet formation, image processing, and so on. And the solution has two physical property. It has two phases. One is phase worsening, one is phase separation, and second one is phase worsening. So the top row is basically phase separation stage where the time is very fast. So you have to capture this first row. You have to do the time steps to be very small, around 10 to the power minus 6, and this one is almost equilibrium. So there is not much change. So there you can relax your time steps a little bit. So what we do is we have so that same cantilever equation can be written as a mixed form. So basically we have introduced a Poisson term, and then it can be written as a kind of mixed formulation. And then we used backward Euler in time to semi-discretize the system like this. And then this David Ayer in 1998 proposed two schemes which are gradient stable scheme, unconstant gradient stable scheme. One is nonlinear and one is linearized. So this is a third, this is a cubic term, that is a nonlinear term, and that is linearized using this event, that is the previous time step, and this is an plus 1. So this is a linearized term. And using this, we'll use this scheme to apply the Dirichlet-Neumann and Neumann-Neumann methods. So these are the algorithms. So this is the Dirichlet step. We take initial guess, and then using this initial guesses, we solve the Dirichlet problem and then a Neumann problem, and then this update step with the help of theta. Theta is a relaxation parameter. So that whatever we have discussed in the earlier case. So this is the convergence result for two-dimensional problem cantilever equation. That theta is equal to half is the best parameter for the Dirichlet-Neumann method, and as soon as this terms b minus a 2b whole to the power k and these terms are less than 1, you get convergence, and you get linear convergence. So this is the numerical verification. That so the first two is for very small time step 10 to the power minus 6, and the second row is for 10 to the power minus 3. As I said that there are two stages. One is phase worsening and phase separation. So one should be very small in time step and one should be very, you can relax a little bit there. And you see that it is equal to half is the best parameter in all the cases, and you get quick convergence when compared to others. So you can see just an overview that if you solve the system, you get the coefficient matrix H, and you just basically use the spectral radius method to get the convergence. So if the spectral radius is less than 1, we get the convergence. So using this basically technique, we got the convergence result. This is the second method, that is Neumann-Neumann method. So Dirichlet step, this is Neumann step, and then this update term for with theta. So with the convergence result, similar. So theta is equal to 1 by 4 is the best parameter, and we get if this term is less than 1 is a convergence factor. If it is less than 1, you get the convergence. So theta is equal to 1 by 4 is the best result. In two steps, it gets convergence, and it will 10 to the power minus 10 tolerance level. Same thing. So this is a small time window, small time steps. This is large time step. Get the similar kind of result. Now you can extend the result to many subdomains as well. For theta is equal to 1 by 4. So this is the result for n is equal to the number of subdomains is 16. You still get theta is equal to 1 by 4 as the best parameter. And this is a table for like a varying from number of subdomains 2 to 64. And also we can vary the mesh sizes 1 by 64 to 1 by 512, and we get that the result is very in equilibrium state. There is not much change there. So in the first step, what we did is we used backward Euler, first order in time step to semi-discretize. You can also do higher order time step, time to be measured. So you can use the second order in time step, and which will be unfortunately gradient stable, but you have to use a stabilization parameter S, and you can follow the similar types of steps, Dirichlet Neumann, and you get the similar kind of result, convergence result. So theta is equal to 1 by 4 is the best parameter, as we said in the green line, and for we vary the number of subdomains also, we get the pretty good result. And so that where we have started that this should follow the energy minimization and mass conservation, that is also followed. So I can skip. So this is a comparison between the two like classical and electron Lexington methods that I can see. So this is a conclusion that we have done some very overview of domain decomposition techniques for their convergence results. So works well for nonlinear problems as well, and the physical phenomena also getting like preserved for in this domain decomposition technique. So there are some references. So thank you.
Any question?
Yes. Yes, so we have so what we have done, Blasov equations. So currently we are doing for the Blasov equations. So it's still like we are getting convergence, but the convergence analysis is little difficult because it is a nonlinear coupled problem. So numerically we are getting results, but analytical we are working on this.
Convert the whole problem to a single problem, or if I take the set of basic equations?
No. So there's the application of this one is optimal control problems. So in the optimal control problem, there is a state equation, there is the adjoint equation. So you can use domain decomposition differently. So state equation you solve it with domain decomposition and then use the result for the adjoint equation. So you don't have to do. So in this case, we have if you combine them in one, then it will be easier task. But if you can work on the two separate equations, multi framework as well.
Any other question? We thank the speaker for excellent presentation. Thank you very much.
Now I request Professor S. Cham to felicitate Professor Matu with the momentum. Thank you, sir. Our next speaker is Professor Anita Tomar, who is the head in Department of Mathematics in Pandit LMS Campus, Rishikesh, and Director, Faculty Development Center, and also the Director of Center of Excellence in Entrepreneurship and Incubation Center. She has published she has done many publications with multiple chapters and has edited book on fixed point theory and its applications to real world problem, and special issue on nonlinear analysis and application, special issue on recent developments in fixed point theory and applications. She is also the lead guest editor in special issue on unique and non-unique fixed points and their applications. She has multiple collaborators in various countries and has organized many international conferences, workshops, seminars and faculty development programs. She is the life member of Indian Society for History of Mathematics, Indian Mathematical Society, and reviewed many journals of repute. She is the recipient of Teacher of the Year Award in 2020, Leading Women Scientist Award of UCOST Dehradun in 2021, and Chief Minister Excellence and Good Governance Award 2020 to 2021 in 2022. Excellence in Research in 2023. She is the member of Board of Governance, Executive Council,
Academic Council, Board of Studies, RDC interview boards, and also the subject expert in UKPSC. With this, I request Professor Anita Doma to please be here.
Hello. Okay. Good afternoon, everyone. First of all, I want to thank the organizers who give me this opportunity. I am also thankful to the chairperson, Professor Martinde from Africa. So today I am going to speak on advancements in fixed point theory, generalizations and applications in science and engineering. I am giving very basic talk because I can hardly any participant from fixed point theory. So I will start with the basic definition. First of all, what is fixed point? A fixed point of a function is a point that remains invariant under given conditions. Means which is mapped to itself. Suppose we are given a non-empty set and P is a single value map. A point y belonging to x is called a fixed point of P if Py is equal to y. Means y remains invariant under the given mapping P. In real life, if we observe the rotation of a wheel, its every point moves except the center of the wheel. So we may compare it to a fixed point. The boiling point of or a freezing point of a substance such as water or any other liquid that is used to calibrate a thermometer or define a temperature scale is a fixed point. If we imagine a hurricane, which is like a spinning top, in the middle there is a white spot like a tiny islet in a stormy sea. This calm point is the eye of the hurricane, which can be viewed as a fixed point. Around it, the storm still widely, causing a chaos and destruction, but this point does not move and we call it a fixed point. The temperature at which thermostat is set is fixed. When the room temperature reaches this point, the heating or cooling system adjusts to maintain itself. This is also a fixed point. In chemical reaction, a fixed point is where the rate of forward reaction is equal to the rate of reverse reaction, leading to a stable state where concentration of reactant and products remain constant. The equilibrium price in financial markets, where supply equals demand, can be considered as fixed point. In computer science, the point at which the iteration algorithm converges to a fixed point. For example, if we talk about Newton-Raphson method, if we find the root of function, the solution is a fixed point of the iterative process. So, in graphical term, we say that the point of intersection of the line y equal to x and the given curve is the fixed point of the function. Suppose we consider a function, simple function 2x equal to x in a set of real numbers. Then we see that the line y equal to x intersected only at one point, and this point is at the x equal to 0, and this is called the fixed point of this function. In another example also, we see if we consider px equal to sin x, in this case also the line y equal to x will intersect at only one point, and the x equal to 0 is a fixed point of this function. If we consider the function 4x into 1 minus x, clearly this function has two fixed points, one is at 0 and another is at 0.75. And this function also has two fixed points, x square, because line y equal to x intersected at 2 points, one is 0 and another is 1. Sin 3x has three fixed points, tangent x has infinitely many fixed points. Cos hyperbolic x does not have any fixed point, because graphically also we see that the line 1 equal to y equal to x does not intersect this curve. Also, x plus 2 has no fixed point, because both the lines are parallel and they never intersect. So, from these examples we see that a function may have a unique fixed point, it may have more than one fixed point, it may have infinitely many fixed points, or it may not have a fixed point. So, motivation behind this talk is, what maps have a fixed point? How do we determine these fixed points? Is the fixed point unique or non-unique? If the fixed point is not unique, then what is the geometry of fixed point? Do these have any applications to real world? So fixed point theory is the most vibrant area of research, and it has applications in diverse branches of science and engineering. The existence of fixed point plays a significant role in non-linear analysis, as many real world problems can be transformed into a problem of finding a fixed point. So Stephen Banach was the first mathematician who gave first metric fixed point result, and he said that each contraction on a complete metric space has a unique fixed point. So one of the significant outcome of fixed point theory is that the mapping under suitable conditions have a fixed point. But this is not always possible. There may arise some situations where the fixed point may not be unique. In case the fixed point is not unique, then it may form some geometric figure. We call such a figure to be fixed figure. Fixed figure means all the points of that figure are the fixed points. So there may also exist a map of figure which map figure to itself, but all the points of that figure may not be a fixed point. So fixed figure have been investigated in metric spaces, as well as its generalization like B metric space, partial B metric space, fuzzy metric space and other metric spaces, exploiting numerous quadratic conditions and is facilitating problem to investigate. These geometric concepts resembles circles, discs, ellipses and various other shapes. And these offers behavior. It is very interesting problem to investigate if the fixed point is not unique and fixed point is more than one. Everyone is familiar with the definition of circle. It is a set of all the points, as the distance of its point from some fixed point is equal to radius of the some fixed number which we call radius of a circle. Similarly, if we replace equality sign by less than equal to sign, then we call it a disk. And ellipse is defined as sum of all the points. So this sum of the distance of a point u from two fixed points, which we call foci of the ellipse, is equal to some fixed constant. If we replace equal to sign by less than equal to sign, we call it elliptic disk. And similarly, we define hyperbola, modulus of distance between 2 points, difference of distance between 2 points is equal to fixed number. Cassini curve, product of distances of a point from 2 points u1 and u2 is equal to some fixed number. Apollonius circle, ratio of 2 points from two fixed points, and k and so on. So maps with non-unique fixed point can play a role in preserving certain geometric figures. These geometric shapes are collectively referred to as fixed figures, such as fixed Apollonius circle, fixed Cassini curve, fixed hyperbola, and so on. For example, if you consider the self-mapping defined as mu equal to u for u greater than equal to minus 3 and mu equal to minus u for u less than minus 3, where u is a real number. In this case, we see that set of fixed point of the self-mapping M is from closed interval minus 3 to infinity. At minus 3 it is closed, at infinity it is open, and we denote the set of fixed point to be Fm. Fm is minus 3 to infinity, semi-closed interval. So in this case, unit circle will be equal to modulus of u equal to 1. Modulus of u equal to 1 means the values in the interval minus 1 and 1. So clearly the values minus 1 and 1 belongs to the set minus 3 to infinity. So it means this set of fixed points contains both minus 1 as well as 1. It means this circle is a fixed circle of M. Similarly, the unit is defined as, in this case, modulus of u less than equal to 1. Means it is from, it corresponds to the interval minus 1 to 1. It again belongs to the interval, semi-closed interval minus 3 to infinity. It means this is a fixed unit is. And ellipse is defined as modulus of u minus 8 plus modulus of u minus 12 equal to 6. And it consists of values. If we calculate, it will come out to be 7 and 30. It is important to note that the ellipse is mainly a subset of the interval minus 3 to infinity, as it contains both 7 and 30. It means that the ellipse with foci at 8 and at 12 is a fixed ellipse. Similarly, we see that elliptic disc, hyperbola, Cassini curve, and Apollonius circle. So we can infer that the set of fixed points of the self-mapping fixed M includes a unit circle, unit disc, an ellipse, hyperbola, Cassini curve, Apollonius circle, because they are all contained in the semi-closed interval minus 3 to infinity. So we call such a figure as fixed circle, fixed ellipse, fixed Apollonius circle, and so on. However, this is not always the case. As there can be self-maps that preserve the geometric figure while not fix all the points of that figure. For example, if we consider the mapping to be defined as 1 upon u. Here we have not included the point u, and the value of m of 0 is equal to 0. So in this case, the map fixes geometry of the circle mod u equal to 1 while not fixing all of its points. So these concepts have been generalized and studied from various mathematical perspectives. These notions differ significantly from those of traditional figures within Euclidean spaces. Here the shape may be different and all other properties of figure may be different. The investigation becomes particularly fascinating and natural when dealing with self-maps that possesses non-unique fixed point. The exploration of innovative conditions ensuring that a given figure qualifies as fixed figure presents itself as an eminent problem of significance in both practical applications and theoretical problem-solving applications. These are some of the generalizations of fixed in rectangular metric spaces, rectangular metric spaces, ambiguous spaces, anti-metric spaces, SP-metric spaces, metric spaces. However, the first result in this direction was given by Nihal Tess and Nihal Osgar, which was given in 2018. However, it got published in 2019, although its generalizations and extensions were published earlier. So these are some of the generalizations of fixed figures which are given by different mathematicians in different spaces. In quasi-metric spaces, partial metric spaces, and using different conditions. From various findings, we can draw some conclusions. Circles and their generalizations in different spaces may have distinct shapes, and these are different from those in Euclidean spaces. Also, their shape can change based on underlying metric. The shape may be different in simple metric space, it may be different in B metric space, it may be different in fuzzy metric space, and so on. So, for detail, one may refer to our papers. These are some recent papers. Additionally, we notice that fixed radii are not dependent on the center, like it is in Euclidean spaces. Also, we note that if M of F means mapping of F under M is F, it does not mean that F is a fixed figure of F. Because as I earlier said, all the points of the figure may not be fixed points. Self-maps may not necessarily fix all the points of a given figure. When a self-map fixes a disk or an elliptic disk, it also fixes a circle or an ellipse, but the reverse implication is not true. Fixed disks and elliptic disks are not unique because all the disks and elliptic disks within a fixed disk or elliptic disks are also fixed. These are some of the papers. If anyone is interested, may read these papers. When the foci of an ellipse like curve coincide, it behaves like a circle. Active action functions are crucial decision makers in neural networks, influencing learning and stability. Common activation functions such as ReLU and leaky ReLU exhibit fixed point sets that include fixed figures. These highlight the significance of fixed figure problems in context of activation functions. Discontinuous activation functions such as lexical hat-type activation function introduce non-linearity and offer high storage capacity compared to other continuous counterparts. These are again some references. The study of fixed figure has been subject of exploration in metric spaces and their broader generalizations involving various contractive conditions. However, there remains an open problem associated with hyperbolas because hyperbola is not closed. So, hyperbolas have two unbounded connected components, making it challenging to conceptualize the notion of hyperbolic disks. So, disks by definition are bounded, and this inherent bound nature conflicts with the unbounded characteristic of hyperbola. It is fascinating question to investigate the conditions under which the bounded connected subcomponents of the hyperbola must contain a collection of fixed point so that this part become fixed disk. So there are some applications of calculation of fixed points in science and engineering. Like in real life, fixed point indicate a situation where a steady state condition or equilibrium is reached. Fixed points are crucial in the design of stable control systems. For example, in an automatic cruise control system in vehicles, the set speed is a fixed point that the system aims to maintain. In digital signal processing, filters are designed to reach a fixed point where the output signal stabilizes effectively, removing noise and otherwise unwanted components. Fixed points are used in power system stability analysis. The operating point of power system where supply meet demand without causing system instability in a fixed point. Fixed points are used in analysis of structure under load. For example, the points where the deformation of a structure under load become constant can be considered as fixed point. In the study of fluid flow, fixed points are used to analyze the stability of flow patterns. For example, if the point at which the flow rate in a pipe becomes stable is a fixed point. In robotics, fixed points are used in design of control algorithms for robotic arms and other automated systems to ensure they reach and maintain desired positions. In the context of gene network, fixed points are often seen as a stable patterns of gene expression on the basis of particular biological processes. In economics, a Nash equilibrium of a game is a fixed point of the game's best response correspondence. This is a result for which John von Nash got the Nobel Prize. In compilers, fixed point computations are used in program analysis. For example, data flow analysis, which is often required to do code optimization. The vector of page rank values of all web pages is a fixed point of linear transformation derived from the World Wide Web's link structure. Logician Solval makes use of fixed point in the influential theory of truth. The stationary distribution of a Markov chain is a fixed point of one-step transition probability function. However, in physics, more precisely in the theory of phase transitions, linearization near an unstable fixed point has led to the mathematical explanation of the term critical phenomenon. This is the phenomena for which G. Canathan got the Nobel Prize. After locating these fixed points in a system, the stability of each fixed point can be determined, which enables engineers, scientists to establish how the system is functioning and responds to future conditions. Hence, the fixed points play a critical role in various fields of science and engineering, providing stable solutions to complex problems and ensuring the efficient and reliable operation of systems. If we consider set of equations, suppose we are given a system of equation in the form Gj, which is a function of x1, x2, xn, where Gj are continuous, and if we consider Fj equal to Gj plus Fj for any point x equal to x1, x2, xn, and we define Hx like this, then x star belonging to set of n-dimensional system is a fixed point of the system of equation. Recently, we used our result to visualize some fractals. We used different fixed point iterations for it. First, we developed the escape criteria using distinct iterations, then developed an algorithm to explore the fractals. Estimation is done repeatedly at a point x and y in plotting region. Depending on the computational behavior, the color of the pixel is selected. The parameters are examined in every iteration to check if the critical state, the escape position is attained or not. If this space is attained, we stop the calculation, sketch the pixel black. Then we examine the next points x and y. The color of every point demonstrates the rate of reaching the escape point. The black color generally demonstrates the parameters which do not succeed to escape prior to iteration limit. On the other hand, the brighter shades demonstrate the escaping points. The points, this provides a visual description of number of cycles necessary to attain the escape state. For the complex region is partitioned into a specific number of pixels. If C is the center of the pixel, we iterate the critical point 0 under PC and examine at every phase if the orbit has modulus greater than 2 or less than 2. Whenever this is attained, C is not contained in the Mandelbrot set and we shape the pixel in accordance with the number of iterations. Otherwise, we keep iterating and then determine whether the variable is contained in Mandelbrot set or nearby it and shape the pixel black. Mathematically, the Mandelbrot set is described as set of all the points for which f of f is corrected. It is a set of all complex varied parameters for that Field-Julius set of z star plus c is connected. Or equivalently, we can say that set of all the points means complex numbers for which the sequence does not converge to infinity as k tends to infinity. Let f be a complex varied functions for z not belonging to c. Let alpha, beta, gamma belong to C with closed interval 0 to 1. Then we know that Picard iteration is defined as z of k plus 1 equal to f of zk. Mann iteration is defined as z of k plus 1 equal to 1 minus alpha zk plus alpha of f of zk. Clearly, Picard iteration and Mann iteration are one-step feedback procedures. And we define Ishikawa iteration as z of k plus 1 equal to 1 minus alpha zk plus alpha of yk and yk equal to 1 minus beta zk plus beta of f of zk. This is two-step feedback procedure and Moore iteration is a three-step feedback procedure. So we notice that if you put gamma equal to 0 in Ishikawa iteration, then we, in Moore orbit, then we get Ishikawa orbit when gamma is 0. And Mann orbit when beta and gamma are 0, and Picard orbit when alpha is 1 and beta and gamma are 0. So some Mandelbrot set as fractals in Picard, Man, Ishikawa and new orbits of the function fz equal to sine of Zn minus Az plus C are explored. Here Z is a complex variable and A and C are complex numbers. So this is the shape which we obtained for Picard iteration. You will notice that in this particular fractal, the number of colors are limited. And here this is also, this shape is also for Picard iteration. And here the value of n is 5. Here also the number of colors are limited. If we choose Man orbit, in Man orbit, the picture is very colorful. It is symmetric about both the axes, and you will notice that there is a small ring in between. This is for n equal to 3. This is cubic Mandelbrot set. As we increase the size of n, means if we change n equal to 3 to 5, you will see that this is again a beautiful fractal, but here the size of ring has increased. So we conclude that as n increases, the size of Mandelbrot set, the size of ring also increases. Again, if we increase the size of n, the size of ring in between has also increased. These are the fractals. As size of n increases, the fractal becomes circular in shape. So for Man orbit, we obtain very colorful fractals, and this is in Ishikawa orbit. So in Ishikawa orbit, the fractal is very colorful, and this is also symmetric about both the axes. And this is again in Ishikawa orbit. This can be compared to fire cracker which our children use during Diwali festival here in India. And as the size of n increases in Ishikawa orbit, the number of colors limits, but the shape becomes circular. This can be compared to our swastik symbol. This is our holy symbol, which is used here in India. So this is quintic Mandelbrot set. This is again a spiral, and these are the fractals in Noor orbit which we obtain. So we observe that in Picard orbit, the number of colors are limited, but in Ishikawa orbit, Man orbit and other orbits, the number of colors are, the fractal is very colorful. So it is again an open problem to discuss that why the number of colors are limited in Picard orbit. So now I am going to discuss some applications of fixed point in neural network. Because the storage capacity of this continuous activation function is higher than continuous activation function, we discuss here Mexican hat type non-monitoring discontinuous activation function, which is used to introduce non-linear properties to the neural network. This is the definition of Mexican hat type discontinuous activation function. For this, we have considered usual metric. If we substitute the values in Mexican hat type neural network, we get this function. Here you will notice that this function has two fixed points. One is at -3/2 and another is at 9/2. And this function is continuous at -3/2 and also at 9/2. And the set -3/2 and 9/2 is nothing but the ellipse having foci at 1 and 2 and center omega 1, 3. So this is a fixed ellipse. So this is the diagram. The Mexican hat type function is discontinuous, but it is continuous at the fixed point -3/2 and 9/2. If we again change the value of constants, we get this activation function. Here 4 and 9 are the fixed point, and this function is continuous at 9 and this continuous at 4. So here the ellipse with foci 6 and 7 and center 13/2 is 4/9, because 4 and 9 are the fixed points. So this is a fixed ellipse, and this is a diagram. Here this is also discontinuous activation function. So we conclude that Mexican hat type activation function is never monotonically increasing. So we may decide The fixed points or fixed ellipse at which the activation function is continuous or discontinuous. So researchers show that maximum human deaths on the earth are due to heart disease, and ECG signal classification is significant for early diagnosis and treatment of cardiac disease. So consequently, we may use these type of activation functions for our treatment in real life problems. So the practical use of obtained results in fixed figure problem can be significant across various fields. For instance, the exploration of fixed figures are useful in rectified linear unit, can lead to improved activation function neural networks. This could result in more efficient and accurate machine learning models benefiting areas like image recognition, natural image processing, and predictive analytics. Fixed Apollonian circle can optimize signal reception and antenna design. This could lead to the improved wireless communication system, radar technology, and satellite communication. Fixed figure theorem can enhance path planning algorithms and object placement strategies. These are helpful in to model electrical orbits and celestial motion with greater accuracy. More accurate position and determination using fixed figure can enhance GPS accuracy. Application in lens design and optimal instrument optimization, potentially leading to advancement in microscopy and telescopes and medical imaging devices are helpful. The concept could provide new insights into stress analysis and structural integrity. So there are so many applications. This can lead to better decision making tools, more efficient algorithms, innovative solutions across wide range of scientific and technological domains. The concept developed might find applications in quantum algorithm, quantum state descriptions, and potentially these are some of the references which we have used. So science and everyday life cannot be and should not be separated. Thank you everyone for your kind attention and honoring me with your attendance. Thank you. Any questions?
Questions? Any questions? Okay, maybe let me make a comment. In dynamical system, the issue of equilibrium points and fixed points, are they related?
Yeah.
They are related.
Yeah.
And the same thing.
That's why he got a Nobel Prize for it.
Yes.
Yeah.
So let's give hands of applause for the speaker.
Thank you so much, ma'am. Next, I will request Professor Murthy to felicitate Professor Thomas. Meanwhile, some of the students of panel sessions are sitting here. They can please report to their rooms. Thank you so much, sir. Thank you so much, ma'am. Thank you all the speakers. With this, I request all of you to please join on the second floor for the tea break. Yeah, in E block, room number E422. E building is.
Go to the second floor for a tea break. There.
Yes, everybody can go to the second floor for the tea break.
The building is E.
Sir,
ଟିକେ ଇଏ କରିଦିଏ ବୋଲେ କାମ କରିଦିଅ ଆଉ କିଛି ନାହିଁ।
Just one photograph. Take from there also. Yeah, that also. Yes, yes. Great smiling, Alex. Thank you so much. So,
होनी चाहिए ठीक है बच्चों को बोल दो लेकिन आप ही के लिए ये कंप्लीट देखे नीचे इम्पोर्टेंट बस इसके साथ लास्ट में उसके बाद हम जाएंगे छोड़ेंगे तब याद रहेगा। अरे रुकूंगा नहीं मैं कहीं पे भी मतलब 3-4 जगह ऑफर है यही की भी आपको ऐसा सेक्शन आपको कुछ फोटो ऐसे लोगों का नाम नहीं याद नहीं आपका गुलाब का फूल फाइनली मिला
सर
आ गया
बंद कर दो
बस अब लाइव सेशन एंड
आप कैमेरा नहीं जान
बस मु सब नौ
कैमेरा नहीं जान तो फिर काली से जो पोटा को रखछन से थुआई दो काली फिर लगियो ना काली